Today I'm going to study compilers and the graphology layouts. Maybe a little bit of reactor fiber as well. So I think on the previous stream I made not a mistake, but I think I confused part of the reactor fiber code because I was looking at the canvas components that they have. As far as I understand now, it looks like they have two different components. One is for the React for smartphones, which uses React Native, and the other one is for the web. And I think I was looking at the one for React Native, which for the smartphones, which uses React Native. So for the one for the web, you don't need the Expo.gl, I think, thing. And I almost managed to make it happen with my own code, trying to just refactor all of the stuff that they did. But I couldn't manage to make it work yet. And because there's 2 weeks for the nights and weekends, I think I'm not sure if I'm gonna be accepted or not, but my plan was to start studying compilers and interpreters 2 weeks before nights and weekends. So I think that what I'm gonna try to, not try, I'm gonna start studying now. And then maybe later on I'll go back to this and try to finish making it happen. So yesterday I made it work with using the canvas from Reactor Fiber, and then I just changed so that instead of using the components, I'm using the 3JS code. But for some reason, this code here, which is like I was trying to refactor everything so that it doesn't use a custom reconciler. But for some reason, this one, it loads a bunch of different times. So when I use Reactor Fiber, it just mounts and unmounts twice. The store that they use to keep track of the state of the rendering. But when I use this code here that I have, then it loads like 8 times. So I'm not really sure what's going on. And yeah. And it's kind of hard because the way that they do it is good for if you're gonna use a custom reconciler, because the way that they set up the functions, it's like it was really hard to think about how to make things work. And I think here I made it work. Also, like, what makes it very hard is the Zustand store, because and a shout out to them because they are very helpful on their Discord. I asked the question and the guy pointed me to this here. And it seems like this stuff is because it's complicated, so I'm not really sure if it works or not. But it seems like for now is decent, like it's good enough. But they changed the version of Zustand, and then the code that I have from the other library, the RiaGraph, is like from an older version. So the way that it works now, like the problem is this here. Like I have 2 different parts of the. If I want to implement 2 different parts of the canvas component, then the question that I had is like, how do I make it so that the store is only encapsulated on the scope of the component and the children's of the component, and not for the other instances of the canvas component. So let's say I want to put multiple different canvas on the website, but then I'm gonna design the canvas component as depending on the Zustand store. So in my mind, this would be a problem, because then, like, every time that I change one part of the website, let's say a user opens one page and they change the state of one graph, it would automatically change the state of all the other graphs on the website, because the components are connected through the store. So the question that I had is like, how do I keep the scope of the store to only the component and its children? But at the same time, I don't want to manually create a different store every time that I want to use another canvas component. So, like, the thing is, I'm not 100% sure because I didn't make it happen yet. I think this is one of the reasons why it doesn't work on my case, because I'm creating a bunch of different stores each time. Like each time that it renders, it creates a new store. And then when I try to use the hooks, it doesn't work to show the visualization. It seems like it works though with the other parts. So what they recommended, what the guy said was he shared this link here. And it looks like this is dependency injection, the name. So they recommend you to use the useRef hook and then create the store based on the useRef, and then create a normal React context and pass the value of the store in the context. But this, it feels kind of weird to me, because then like it's like you're using the Zustan storage so that you avoid using the normal context because it's better. Because what the Zustan store does, as far as I understand now, is it optimizes the amount of renders that you're gonna have. But then, like, if you're gonna use the Zustan to avoid using the normal context, then why use the context here to solve this? Like, it feels kind of weird. So this is the stuff that I don't understand really well yet. It seems like it is working here. I think it's on the other project. I made so many projects about this that I don't even remember very well which one is which. But yesterday I made it work in the simplest way, and then I changed the repository for the main project, and then I deployed again, which thank God was very easy. I just changed the Git file, and then I recommitted everything, and like I made it so that is the, let's say, simplest version possible that works. And then I deployed, and everything worked first time. So, but I'm still using the Reactor Fiber canvas, not using the one that I was building here. So I'm trying to think about, like, where did I put the... I think it was this one, maybe. There's so many things going on in my mind, so it's kind of hard to explain everything that I'm thinking about. I think it was this one, yeah. I just changed the canvas that I'm using, yeah. So I was building the custom canvas that is not going to use the custom React reconciler, and I was just trying to refactor the code from Reactor Fiber to make it work, but for some reason the hooks weren't working. So I think now what I'm gonna do is study the layouts. From Graphology, because I think that I'm not 100% sure if it's working. And then after I study this, I'm gonna start studying compilers and interpreters. So the way that it works here, maybe I should go over the Reactor Fiber first. Problem is that it's gonna be kind of annoying. Oh yeah, that's what I'm gonna do. I have the project locally, so I think it's here. I think that's what I was trying to open. Because if I could just go through the code here, it's just gonna be one file, so it's different. So I think I'm gonna go over the Reactor Fiber code from the project, like from the source code. I think it's here. Then explain what I was thinking about, like how did I change the stuff. how did I change the React fiber code so that it works? Like, it's working, it's rendering the canvas, but it doesn't render anything because of the hooks. And I couldn't figure out the hooks part yet. I'm just gonna go over this and then I'll explain how it works. And so this is the stuff that I talking about. They have the native here and they have the web. And I think I was looking at the native because I didn't realize that there's two versions. So this thing here, it felt weird to me because I knew that React Native is for the smartphone. So it uses this view and this Expo.gl, but I think that this is just for native, which leaves me with more questions as well, because obviously ideally you want to create a website that works in both cases. So like I don't understand really well how to make that happen. Maybe there's a way that you can get based on the like the window object or something like that. You can figure out if the person is using a smartphone or using the web, and then you can make a condition to use either one of the components. But I think that's it's a lot of work, so I'm gonna focus on just the web for now. And I also think that for the stuff that I'm doing, it doesn't make a lot of sense to optimize for smartphones, but maybe it does make sense. Just like in my mind, I would never use it from a smartphone, but I think that there probably will people that will want to use it, but it's just a lot more work, so it's kind of annoying. So this one uses the gel view, which comes from Expo.gl, and this view that comes from React Native. And this one, it just uses the reference to the canvas, creates a normal canvas and a div, and then uses that. And this fiber provider just is something that comes from a library called It's Fine, and what it does is just, there's a variable in React called React internals, I think, and if you're gonna create a custom reconciler, I think you need the React internals variable for the create container, which is gonna be the root of the custom reconciler, which is just a React element. So you call the function create root, and then you pass HTML element, and then from that is gonna return an object, and that object is the object that React uses to mount everything on the fiber. So in that object, I remember when I was trying to do it with Pixie, and it requires at some point in the flow of the functions in React, in the React reconciler, that the object has this React internals variable. So I think that's the reason why they wrap over with this thing here, which provides the React internals as a context. And then this wraps the other component, which is this one here, the main one. I think I'm gonna explain this, how it works, and then after that I'll go back to this one. Because there's two things that I have to figure out. One is the context, which I think is gonna be relatively easy. You just create a component and then you set the values of the store based on whatever you put, and then I can put flag variables to decide whether or not some parts of the component are gonna show. But I think ideally, like I would allow for customizations on everything on the graph, but the part that is gonna be a lot more complicated is the part that is related to the visualization of the code, because then it can be like there can be very complex things that I could do with customization, and I'm gonna have to see how to make that happen. Depending on how do I structure and like how do I figure out what is useful to structure the information from the code so that I can visualize and make it easier to understand what's going on a complex software project. Yeah, so let me go over this one first. So this, I think it just puts the tree JS it extends React Fiber to have all the objects on 3JS from React's perspective, I think. So I'm not 100% sure how the extend works here, but I think that it is because of the custom reconciler. Like what it's doing is allowing the custom React reconciler, which is the React Fiber, to have access to all of the objects on 3JS. I think that's what this does, but I'm not 100% sure. Then this context bridge, I'm not 100% sure also, but I think that every time you use a custom React reconciler, you need some way to pass context from the React DOM reconciler to the custom one, because React doesn't work with the context like that. Like if you have custom reconcilers, you can't pass the context from one reconciler to the other. So you have to use something that is called a context bridge, and I don't know very well how it works. I just saw in the Pixie documentation they have something that talks about this. So I assume that this is what it's doing. Like this is the purpose of this thing here. But I think it's not very important to the stuff that I was trying to do. Then this is another library from React that I haven't seen, but I think it's just for analytics. So React use measure, and then it gets the wrap for the canvas and the div that wraps the canvas. Then it creates the wrap for the root. And I think the reason why it creates the wrap is so, like the name says, it keeps a reference, because the way that the reconciler, the way that React works with wraps is different than with the state. I think wraps are maintained throughout the cycle and state is updated every time. And then it uses this use isomorphic layout effect, which is just a function that they created that decides whether or not to use the use effect or use layout effect, which are two different React hooks, to depending on some condition, some if condition. I don't think it matters that much, to be honest. Then they get the wrap for the canvas, and then this is the function that I'm talking about, that in their case they created like a custom function, so they are wrapping the React reconciler create root with some extra logic, I think. But then they pass the canvas reference to this function here to create the root.current. And then here they keep track of how many roots the thing has through a map. And this is, I think, the part that I'm not 100% sure if I understand very well how it works. But I think what this does is prevents multiple different roots from existing. So they get the canvas if from here. If it doesn't exist, it's going to be undefined, I think. And then the canvas has the root, which is the map there that I just showed, has the fiber and the store. So they get that from the canvas. And if it exists, they're just going to use that. If not, they create the store. And this is the top container, I think, the parent container of the custom reconciler, called the create container function. And you pass the store. So the storage is the children. The concurrent root is just a flag variable from React that is going to determine that it is a concurrent root, which is different than the... I don't remember the name of the other one, but the concurrent is like the name says. It allows for different things to happen at the same time, I think, depending on the scheduler and the lanes. And the other one is more simple, but then is less efficient, I think. So they put this concurrent root at the top. This is going to be the parent of this, and they pass the store as the child. And this is going to be the top of the custom renderer. And this is the thing that, I mean, that is kind of hard to understand, because like it involves the whole life cycle of React, the whole mapping here. Because this means that it is only going to create one root, because every time, like after the first time, it's just going to get that root. But then the issue with that is that like how does it work with the whole application? Like the problem is this thing here that I don't understand very well how it works. Because inside of this, they are using a Zustand store inside of the custom reconciler, which is this part here. And the store changed. I think that on Reactor Fiber, they are still using an older version. So I think this is the part that I'm struggling to understand. So here in this file, they create a normal React context, and then they create the store. So this is the function from Zustand that is going to create a context from Zustand that is going to allow you to manage the state of everything related to the rendering thing. So they get the position, create these functions. And these are all the attributes that are necessary for rendering. This part is kind of hard to understand as well, but I think it's related to the loop, to the rendering loop on the request animation frame. So I think that when you call this subscribe here, it's like the name says, subscribes some logic to run inside of the request animation frame. But I don't understand really well how it works. So this is the part that of the store. So they create the store here, and it has all these attributes. And the way, as far as I understand, the way that the Zustand store works is it's going to accept a setter and a getter, which are these arguments here. And then every time you create the use store hook, you can pass the state of the store, and then the second argument is going to be the new state. So usually I think you pass an object as a second argument, and the object just says like which property of this state here is gonna change. And then it does a shallow copy, not a deep copy. A shallow copy is only gonna copy it copy the references, but it doesn't copy the full object. So it just creates a new reference for the previous object. So if you wanna do a deep copy, they provide other libraries as well. And then here they got the state of the store, and then they call this subscribe and pass some stuff here. These parts I still don't understand very well. And this invalidate function, also I think that this is related to the problem I was having before, because I remember having a mistake related to this. And this comes from create loop function, I think, the invalidate function, and some other parts of the code. It comes from this function here, yeah, this invalidate. So at some point it calls this function here, which creates these three different functions that are going to be related to managing the request animation frame. So I think what these functions do here, the create loop, they are functions that allow you to manually change the request animation frame depending on what you're going to do. I think that they are related to the problem I was having, but still haven't figured out what is going on. Yeah, then it returns the state, which is the store. See if I'm still here. So it creates the custom reconciler, and then this function here, which is the one that is being called here. So the root.current is gonna return these three different functions here. And this is kind of annoying to understand, but pretty much what they are doing is just passing a bunch of configurations, and that's the part that was kind of annoying to refactor, because the logic that they are placing inside of this function here comes from a lot of variables that exist outside here. So mainly the store, I think. So they initialize the store and the root fiber, which is going to be the top of the fiber reconciler. And then they make these functions based on these values here. So I was trying to pass this function to the canvas, but the problem is that I had to pass the other variables as well, because otherwise these functions don't have access to the variables. But what this does is just configures everything in the beginning. It initializes the store values with these configurations here that you can pass as props to the canvas. So gel is going to be, this is another part that is confusing. Gel is not the renderer. Gel is just the options that you can pass to the renderer. So if the first time that it's running is not going to exist, so like it's going to return these functions here, and then after here is going to call this right away after it creates with this object here that comes from the props of the canvas component, which is the canvas implementation. So it passes these props here to this function here to initialize everything. So if it doesn't have the gel, it's just gonna set on the store. The state is the store, the Zustan store, and then it calls the set function. And this is what I mean, that is gonna, this function is just gonna copy the state of the store and change the object here that you pass as an argument. And this one creates the render from 3GS, passing the configurations here. Then it creates this raycaster, which I think that the raycaster is used to keep track of the objects on the scene, so that you can create events, I think, like drag events. This apply props is kind of annoying. I didn't spend a lot of time trying to figure out as well. But apply props, I think, is related to the reactive compiler, which is a function that allows you. So the way that it works, it compares the two different states of the DOM, the virtual DOM, and then depending on whether or not there was some changes, it's gonna call this function apply props to create the effects or apply the effects that the props have. Then it creates the camera here and sets the camera to the state. The scene sets the scene. This is some stuff for VR that I don't really know very well. And it's not, it doesn't matter for what I'm trying to do. It puts all the other configurations here, apply props. It's pretty much just the initial setup. And then it returns this, and then right after this it's gonna return the render. So we're gonna call the render inside of the use layout effect. And this is the part that was the most annoying. So here it's gonna pass this component to this function here, which is this function here. So it passes those components to this function, and this provider is another component, is another function, and which is a component. So here the update container mounts the elements to the root fiber, which is the one that was initialized there in the beginning. So it's just appending the children, which are these components here, to the main fiber, to the main component, which is the root of the custom reconciler, which is the fiber. And the way that it's doing that is kind of annoying, because here is the thing that I talked about, where it's receiving the store, it's passing the store here, but the store was initialized like outside of all these functions. It's initialized here on the scope of the create root. So to separate this container, because the problem here is it works because they're using the custom reconciler to mount. But if you wanna just mount with the normal React DOM, then it's kind of hard, because then like how do you put these components as children of these ones here if you don't have access to the store that comes from the other function? That was the problem that I was having. So I think this is one of the main reasons why I had an issue there on my implementation, because the way that I do it, the way that I did it was just to copy all the logic from the functions inside of this one and I put inside of the use layout effect. So this is the issue. I think this is the issue. And then instead of mounting here through here, I just put this fiber, this provider here, like inside on the return statement of the canvas. So it's different. But what this does is just wraps the store with the context for the store. It wraps the it's just pretty much the main components. So it's gonna be the fiber root, which is the create container from the store, and then right below that's gonna be the context provider, which is the normal React context, which is this one here. So it just creates a provider for this and passes the store. So it's a normal React context, and the value is going to be the store, and then the parent component of this one is going to be the fiber, which is a create container from the store as well. So just pretty much creating a concurrent root, mounting the store as a child, and then as a child of the store, it mounts the normal React context and passes the store as a value. So what this does is makes it so that the state of the React fiber is going to be managed by a Zustand store. And that's pretty much what the custom reconciler is, I think. And then obviously they put some configurations on the custom reconciler so that you can add 3JS components. 3JS has components inside. And then the issue with using that is that you can't use normal HTML unless you use a tag, special tag that they have, I think. And then the other issue is the context bridge, and also that it couples more the stuff that you're trying to do with React state management, which can be annoying. So I'm gonna try to move to like using a custom, like using a normal React DOM instead of using the custom renderer. And so the way that I did it was just putting on the return statement here, and I didn't use the fiber provider as well from the it's fine thing. But here, instead of the provider being inside of the function there on the render, I put here, and then I just copied the logic for the functions on this component, and then I had a bunch of problems. And it still doesn't work 100% the way that should work. Maybe I can just change here to show. I think the stuff that is not working is the hooks, but I'm not 100% sure why. But I think I'm gonna focus on the graphology stuff first and the custom components, because this works. So maybe I would just leave this for way later on after I already study everything else that I need to study. Hooks can only be used within the canvas components. Yeah, I didn't like this thing about the Zustand store. I think that the people that are responsible for creating this library and the other ones are very smart and they know what they're doing. So like I don't think it's bad. The code is just that it feels weird to me and I don't like it. The way that the Zustand store is set up here. Because of the thing, which makes me think that there might be better ways to deal with this, but it might be just a consequence of the way that React is designed. And also, this got me thinking that which, like, up until this point I didn't think about this stuff, but now, like, the more because I'm gaining more experience, I realize that, like, one of the biggest reasons why stuff might be the way that it is today is because, like, the whole environment forces you to update stuff and deploy stuff as fast as possible, and because reality is too complex, so people don't have time to figure out every single thing and to make the code perfect before they update. But then what happens is that it's kind of like you're creating a pile of garbage, because, like, for the perspective of the person creating the code is very good, but they can't organize themselves with everyone else. So everyone's just doing, like, their own thing, and for their perspective, like, on the code that they're doing is very good, but on the aggregate of everyone else's, like, putting together the code, it becomes really bad, because it's very hard to achieve coordination. And I think this is, like, one example of this. I think this is the reason why this is a problem, is because things are, like, built up as a consequence of everyone building a bunch of stuff at the same time, and everyone has to ship fast. So it creates the situation where, like, the errors compound, but it's very hard to make it better, I think. So the feeling that I get is that there's probably much better ways to do this, but I think it's probably, like, a consequence of the way that everything evolved over time. So it makes sense for things to be the way that they are. There's, like, duct tape solutions on top of the duct tape solutions. And the duct tape solutions make sense. It's not that, like, the code is bad. It's just that it's very hard because everything is very complex to refactor everything. And to think about everything from, like, a clear beginner's perspective, let's say. Like, let's say if you had, like, a clean slate and you forget about everything that exists out there, and then you just start from the beginning, but after knowing everything that you learned, then I think that the same people that built React and built these libraries would create something much better if they, like, could forget, let's say, everything that exists already and just build something from scratch. After they learned what they know now. So yeah, for my stuff that I'm trying to do, I'm not really sure what to make of it, because I don't think that it is gonna be worth it to try to use another React context or, like, the other libraries. I think it's much better to just go with Sustant and, like, maybe figure out later. And the thing is kind of annoying, like, is that I have to start studying compilers now and interpreters, but my mind is still on this stuff. Like, once I start working on something, I want to finish, and it's very hard to stop thinking about it. So, but I think I'm just gonna have to. I'm gonna close this. Maybe I will explain the hooks here. The store also uses the context that is created here. They use store hook, which I think that is because they are using an older version of Zustan, but I'm not really sure. And the use tree hook is just using the store here, which is gonna use the context, the normal React context, that is the one that wraps the everything here. So you access this context, which is gonna be, the value is gonna be the store, which has the state for the whole application. And this part I didn't understand really well as well. I think this is another thing that I just erase everything, because it's very annoying to do with TypeScript, and I think that some of this stuff they can do it because they're using TypeScript. So I think that here is, for example, is an optional condition here, which makes it so that you don't have to pass this second argument. It's just optional, but the only reason why you can do this is because it's on TypeScript, but I'm not 100% sure, maybe not. Maybe just if you don't pass anything as the second argument, JavaScript doesn't complain, it just makes this undefined, but I'm not 100% sure. So yeah, this pretty much allows you to, using this hook allows you to access the state of the store, and then you can change the state based on this. And the store is just the values here. Just an object with the values that are the configuration, and then whatever the configuration is attached to. Is this object here. And the use frame is kind of difficult to understand as well. But I think it just subscribes the callback function you pass inside of the use frame to the store using this function here, which is the one that I said is kind of confusing. It's this one. So I think that's what the use frame does. It calls this function, and then whatever callback you pass is going to be this graph here. So it's going to push this graph to this array here, which is an array of subscribers, which I think is callback functions that are going to run every time that the request animation frame runs, which is similar to the way that the Pixie one works, I think. But Pixie works with the listeners. You connect listeners to the ticker, but the overall principle is the same, I think. Just allows you to subscribe as many callback functions you want inside of the request animation frame loop. So I think that's about it for Vector Fiber. There's so much stuff in my mind, it's kind of hard to explain everything, because I'm talking about this and thinking about all of the other stuff. So I think what I'm gonna do now... so here the only difference is I follow the tutorial that they passed, and then I'm creating a normal context again, and this is gonna be for the graph, for the store that is related to the graph. So there's the store that is related to the canvas, which comes from the custom React reconciler, which is gonna be the canvas. And that's gonna manage the state of the rendering, which is the camera, and yeah, the camera and just the rendering and updating of the camera in relationship to React. And then there's the store of the graph, which is this one that I created following the tutorial. And this is like, I changed from the way that it was on the other library, because the other library was using a previous version, and I'm not 100% sure if this is gonna work or not. So yeah, but this is what I have right now. So I use a use graph, and then I create the store here, which is just the code that I copied from the other project. It's gonna have the state of the graph, the variables for the graph. And then I create a normal React context, and I pass the value as a store, the same way that React reconciler does. And then I'm passing this as child, which is the main component. And then the annoying thing here as well is that I couldn't find a way. Actually, you can pass just like specific arguments for the store itself. Because let's say you want some additional setup, some default props or something like that, to pass as arguments here, which I believe that this store has, these arguments here. I couldn't figure out a way to just pass these arguments to the store here. Because obviously I can do like pass them manually here. Let's say selectors, which is one of them, and then just put the ones that are necessary here. But then the annoying thing is that, what if I don't want to pass, like what if I don't want to specify? I just want to pass like a generic arguments. But I guess like what you can do is just put like default values here. So it's not that big of a deal, I think. But yeah, pretty much I call this function, which is gonna call this one, is gonna create the store. This one calls the Zustand one, you create from Zustand. And then you have to wrap the the context that the normal React context that I created here, which is going to be the provider here. I create this function that calls the other context and then makes the store out of this, because the store is going to be the value. And then I just return the use store, which comes from the Zustand. And this allows me to use this custom hook, which is pretty much the same thing, but that's the hook that I'm using now. And this is going to access the state of the store. And this first function comes from the other project as well, which is going to be just a function that is going to pass the props that I receive here, which are the graph specifications. And this is the one that I'm going to study now, I think. But pretty much what it does is just access the values based on the store, and then it's going to initialize the values of the store based on the props that it receives, which are mainly the nodes and the edges. So the component receives the nodes and the edges, and then based on the nodes and the edges, it's going to initialize the graph on the store. And the store is going to be the thing that manages the state of the graph. And the way that it does that is by calling this function to initialize the visible nodes and edges first. And then it's going to call this function here at some point to set the nodes and edges as the result of this function here. And I think that's what those functions are, the ones that I'm going to study now. But the reason why they did it like this, I think, is just setting up a bunch of effects on this component, so that every time that there's a change in the graph, it's going to render only the part that is specific to that value, I think. So separating into multiple effects makes it so that you can separate what's going to be updated every time there is a re-render. So that's why I think that they created a specific component for this and initialize everything on the graph. And then after that happens, then I add here inside of this one, I create the camera controls, which are the thing that is going to allow me to move the canvas. And then I add the graphics that I created when it runs this function here that builds the graph. Like it's going to run the build graph function at some point here, which is this function that is going to receive the nodes. And it's going to create a graphology graph based on the nodes and edges that comes as props. And then these functions I made, which I'm using 3JS to create the graphics. Yeah, I'll be right back. Yeah, that was a lot. It's hard to think about because like I have the stuff that I want to do now because obviously I already thought about all of this stuff, and then like it feels like I have to explain everything that I already thought about. So, and because there's like a bunch of stuff that you forget, like there's a lot of stuff to talk about. But I think that pretty much this is the main difference from the stuff that I have now and the stuff that came from the library. And also I tried to implement the library itself and I was getting an error, so I'm not really sure. I think that is because of the resistant version or something like that, that it wasn't working when I tried to implement the library directly. So I'm glad I did it this way. But I think the main difference is that I'm just using the 3JS objects and they are rendering with the React components. And the biggest issue with rendering with the React components is that it becomes like very annoying to create stuff, I think. Because the main issue is that like to manipulate the graph and to do a bunch of things based on data that you receive, when you make it so that you have to render with the React components that come from React Fiber and React Ray, it forces you to put the code inside of the return statement of the other component, and then it's kind of annoying. Like it feels a lot better to just have the objects themselves from 3JS, and then later on if I want, I can even customize these objects as well and create my own shaders and stuff like that. So it feels a lot better to do it this way, I think. So here what I'm doing inside of these functions is just creating the graphics and then putting the graphics as part of the object that I receive from the node. Here. Nodes and edges. And then when I add the object to the Graphology graph, the Graphology graph is gonna have access to the graphics as well. So the way that I was trying to do before, I don't remember really well, but I think I was trying to put in another place these parts. I was trying to add the graphics after to the Graphology, I think. And I think this way that I did now, it makes a lot more sense. Because that way the Graphology graph already receives everything that it needs. And also I think that for this part of the visualization, there isn't much that I have to do after this. Because as long as the thing is that I can put the objects for the nodes and edges are the bridge between the two, I think, between the way that I'm gonna parse the data coming from the code and the visualization. So as long as I make and obviously the store. So every time that I wanna make a customization on the nodes, all I have to do is create a new value on the store and then create a new value on the nodes that is gonna be optional. And then I can modify the custom component so that it accepts the value as well. And I think the custom component, the way I'm gonna do is just pass a bunch of stuff as props and then do conditional statements to like allow which parts of the component are gonna show the customization components, and then based on that it's gonna change the way that the visualization looks. Hopefully the way that I explain is understandable. Everything. So I think this is gonna be... I'm thinking about going over with the debugger, but it might be very annoying because of the way that the debugger works. So I don't wanna like go over the JSX elements. I just wanna go over the parts for the logic of the graph, but I think that like there isn't an easy way to skip the parts of the JSX. I can change some configuration there, I remember, and then it doesn't show some of the code, but then it doesn't show the part that I want as well, so I couldn't find a configuration that just allows me to see like the parts that I want and then doesn't step over the JSX parts and the React parts. Like I want to skip all the React parts, which is annoying because... And I think this is what I mean, like every time there is an update on React, it's gonna go over the whole tree, and then there's a bunch of loops, and it's very annoying to just step over them. So this is the problem here. But what I wanna do is just understand, because I have a feeling that this stuff is not working. I think that the reason why is because like if I change the layout, it's not gonna change anything here. So I think what this is supposed to do is, based on the layout, it's gonna use some D3 functions that are gonna determine like the position of the nodes. Oh, the other thing that I have to do is implement the drag. But I think I'm gonna do this another time, maybe off stream. Probably just gonna use the Raycaster from the store, and then I added an event listener here, I think, to the canvas or something like that. I think that's what I'm gonna do. But if I change the value here, it doesn't change the position of the nodes. And I think the way that it's supposed to work is you pass the layout, and then based on some function there, I think this one is gonna call this one, which comes from D3, I think. Some of these functions come from the D3, and this is gonna determine the position of the nodes. But I think it does that based on some data property of the nodes, which I don't have, and the examples that they have don't have as well. So this is the stuff that's kind of weird. Like, how does it work on the examples that they provide? But it seems like it is not working here. That's the problem. So I have to understand these D3 functions as well.
The mystery of life isn't a problem to solve, but a reality to experience.
Sometimes I wanna quit doing this, because it feels like I'm putting a lot of effort and like it doesn't not getting any results, let's say. Because but I know that like I am making progress, but it's just like it's hard to visualize the progress, because, and this is the part that is frustrating, because like all of these things are very hard, but you take them for granted, because it seems like it's something that it should be easy to do, like just visualize the thing. So this is kind of annoying. And it feels like there's so many things to think about, so it feels like it's kind of impossible to do, because there's so much stuff. But hopefully at some point it's gonna work, because I do feel like I'm very close to making it happen. I think once I figure out like the visualization and stuff like that, then I think it becomes a lot easier from that point, because then like there's a lot more that I can do, like there's more flexibility, I think. But it's definitely very hard and annoying to do, so. But the thing that I am happy about is that, like, ever since I saw this the first time, like when I used VJS for the first time, the PyVs there, like I knew that I wanted to do something like this. Like the first thing that I thought about that time is that, like, I wish I knew how to manipulate the graph and how to manipulate the visualization to do what I want, because then after that point I think like there's so many different things you can do. And the main challenge is understanding how to have complete control over the visualization and what's happening. So maybe I should go back here and try to see. I know that it's gonna call this thing here in the beginning on one of this. I think it is this one. I think this is the first effect that it calls. I think the use layout effect is run before the other ones. So here it just initializes everything. This is kind of annoying as well because I don't understand how this functions. I think in the beginning this is just gonna be null or undefined. It's not gonna run this. And then it's just gonna be all the nodes and edges because there isn't any hidden ones, but because this collapse ID is the state from the store, and the store was initialized, so I think that this is gonna be an empty array. Yeah, it's gonna be an empty array in the beginning, I think. I think the reason why they put this is because there are some examples that you can click the button and it's gonna collapse the nodes into one node. Maybe I should open the actual library. The other thing I can do is just test a bunch of things here. Like change the values here to see if anything changes. Yeah, I think I'm gonna see with these examples here. Like what happens when I change the layout type. I think the layout type is the thing that determines, is the prop that determines what layout's gonna be. So we should change the positions of the nodes and the edges. So let me see. When I change there, then I'm gonna go over this, I think. I'm gonna see, like, as if I'm stepping with the debugger to see if I can understand each function that it's using. Then after I spend some time doing that, then I think I'm gonna go over with the actual debugger to try to understand. It seems like it does change. I think it does change a little bit. Maybe the circular one's gonna be better. It's like more. Let's see. Yeah, it does change. So now I'm gonna test on my stuff. And I think it's not gonna change on... I think I already tested, if I remember. So yeah, it's gonna be here. Actually, I need to run the thing first. I think it's not working. So this is the thing, is because the library, they use the React Spring. So it's something that is going on with React Spring that allows them to change the positions. And this is the stuff that I have to understand. It's also kind of weird here. It's not supposed to move like this. And now it's moving correctly. That doesn't change anything. And when I save, it fucks up the controls. So I think it's because of the way that I'm initializing the controls. Or maybe if I initialize outside of the use effect. Maybe that's the problem. Ah. Or if I just remove this thing. Oh, fuck. It still fucks up. Maybe I have to... But I think I can't initialize this inside because of the use frame, and I can't use the use frame inside of the use effect because it's a hook, so... Yeah, but now it seems like it works. Yeah, so I think it's probably better to initialize outside. So this way it works. Yeah, don't understand really well. I think I'm gonna leave it like that. But the problem is I don't know. And there was some parts, like some instances before when I was doing different things that this happens as well. When, like when you control save, it does a hot reload, and I'm not really sure what is the difference between when it does the hot reload and when it runs the application, but I assume that the difference is on the way that React's gonna render the components. But I don't understand the nuances of it, so I don't know really well why the controls mess up there. I think that the reason why is obviously because it was inside of the use effect, so probably the component doesn't mount or unmount, but the use frame continues to update, so they become out of sync or something like that. And then the controls mess up if I initialize them out inside of the use effect. So what I have to understand is how does it... Maybe I should follow the layout type. One of the annoying things of understanding this is that it passes a bunch of stuff through props, and then it uses this like spread operator to pass, so it's hard to track at what parts is using the thing. It passes here. Yeah, so mainly on this function here. Yeah, so initialize everything, then gets the nodes, creates a reference to a drag, and this is for the use drag, which I don't have because I'm going to use the raycaster instead of using because they use React gesture, I think, use gesture, something like that. It comes from the same group that created Zustan, but I think I'm gonna use it with use the raycaster from the Reactor Fiber from the store to try to create the drag events. And I'm probably gonna do something similar here. I think like I'm gonna use Raph as well, probably. I'm not sure. And declare this function. Inside of this function they call this one. and pass this one here. And this part's very confusing. Also don't understand this very well. I kill this in frame, so it only happens after the graph is built. Like, what do you mean by that? Because I don't understand, like, how this is gonna work with the cycle from reactor fiber. I think this is one of the issues here, is that I don't understand really well how... At what point reactor fiber initializes the rendering cycle, I think. The first request animation frame, and how does the... like the other ones that you can subscribe using the use frame, how do they work? Yeah, but I think that the first one that is gonna run is this one, obviously, which builds the graph. And this one is just to update the layout. So if there's already one mounted, it updates. In the beginning, layout mounted is gonna be no, I think, or undefined, because it's a use ref. Yeah, we use ref false, and then it's gonna update inside of here the first time. So it's either equal to the one that it passes, or it's gonna call this function. Let me go here. Yeah. The first time doesn't pass anything, so it's gonna call that function. And the only time that it passes is when it already has the layout. So after the first time, it sets up the layout should be equal to that function, and then it's just gonna use that all the other times. I think the main part that I'm struggling to understand is the request animation frame, I think. And I think the problem is that I don't understand the way that reactor fiber sets up things. I think you have to call use frame at some point, otherwise it's not gonna render anything. So I assume that's probably the way that it works. So let me, yeah, because I think I remember not putting anything here and nothing really shows there. So I think that the use frame is the stuff that initializes the request animation frame, and it does that based on the subscribe thing that I talked about before, where it's just gonna push the callback function you pass to the use frame to the array, which is part of the property that is one of the parts of the store, the state of the store. And that's gonna call the request animation frame, I think, at some point as well. I think it maps over the subscribers and then calls the request animation frame or something like that. Also, it does render, but now, yeah, I don't have the controls, so it does render. So let me comment this one out, just see. It's here. It's gonna build the graph, and the graph has the... I think when it builds the graph... Yeah, but then... I have to study more to understand at what points. Oh, so now it doesn't show anything. Interesting, so I think... Yeah, probably reactor fiber doesn't start the request animation frame. But all you have to do is call request animation frame at some point, and then it's gonna render. Because it sets up the canvas, obviously, sets up the WebGL context, but yeah, I think that request animation frame is linked with the WebGL context. And then because React Fiber initializes that, then if you call request animation frame at any point, it's just gonna start the visualization. Because I'm putting the 3JS objects on the scene. React Fiber sets up the scene and everything, and then I put the objects inside of the scene based on this function here, which runs when the component mounts, because it's the first one that runs there. This one. And then this function puts the thing, creates the graphology graph. So let me comment this out and then see if I put this on the main thing, if it's gonna run. I think it is gonna run, probably. It's part of the thing is annoying. Interesting, so it doesn't show anything. That's weird. Maybe it's because yeah, it's because I'm putting the mounts. So maybe it doesn't have anything to do. It's gonna be false there, I think. Maybe. Yeah. Oh, but now it doesn't show. So it's probably just because I'm putting the dependency as mounted there. So this just runs. Let me erase this. So yeah, it still runs. So React Fiber does set up the visualization first, but I don't understand very well how. I think it must be in one of those functions, the subscriber function, or on the create loop that creates the invalidate and the advance to create the store. I think I'm gonna go back to that to see. Maybe this is the most important thing to understand first, because then if I don't understand this, it's gonna be hard to understand the other parts. But I think I'm gonna put like this. Oh. Also, I think it's pretty clear that the use frame allows you to put the callbacks inside the request animation frame. The other request animation frame probably doesn't have anything to do with the visualization itself, like with the React Fiber. I think what it does is just adds a callback function to the request animation frame, and then because both React Fiber and WebGL is connected, like React Fiber is connected with request animation frames through the WebGL context, I think. So I think from the browser's perspective, it creates a cycle, which is the painting cycle, and the painting cycle is gonna have the request animation frame, which is gonna allow you to determine callback functions that are gonna run every time there is a paint cycle, I think. And then the WebGL obviously uses the request animation frame as well, and then React Fiber also uses the WebGL, so I think that it has connection through that point. But I'm not 100% sure how does it start the visualization in the first place? In the very beginning. So I think the only thing that this does is just puts this callback function here at some point in the line of the stuff that is going to be executed. But I don't understand this comment here very well. Give this in the frame, so it only happens after the graph is built. I guess they're referring to the state of the variable here. So they're only gonna make mounted equals true after the graph is built, because they're passing this inside of the request animation frame loop. So it's like they are setting a callback. It's like setting interval or timeout is probably the same concept. So they make this asynchronous. I think that's what's happening here. Because the way that Node.js works, I think, is just like it's single threaded, but it has the event loop, which is separated from the main thread. So when you have set timeouts or promises and request animation frame and callbacks, it's gonna go into the other loop of the browser, which is the micro tasks, I think. And then the first part that is gonna run is the main code, which is this one. So I think that if you put this outside here, there might be situations where the graph's not gonna be built and this is gonna be true. I think that's the reason why they put here inside. But I'm not 100% sure about that. So I think I have to understand more how does it initialize the first request animation frame. How does Reactor Fiber initializes the loop first? And I think it's on the beginning there, because when it initializes the store, I think it passes the should functions that come from the create loop, I think, the advance and invalidate. So I think at this point, when it initializes the store in the first place, on this function is gonna create the loop. So it's passing the roots, which is the map that contains the root that comes from the custom reactor compiler, and then it declares these three functions here. This is the problem because it doesn't. Yeah, this one sets up the request animation frame. So probably this one is the one that starts because it's gonna run as a callback. So this is the effects and this is a timestamp. Don't understand where it comes from, the effect values. So global effects. It's gonna be. I don't understand because it's passing a string there. So. Oh no, the second. This one doesn't come from the function. That's why. So this is a set. So it probably initialized this at some point outside of this function, and then once this runs, it already has the effects. But the thing is that it's not calling this function, so you shouldn't. it's just gonna return the functions, but here I think it also doesn't call the loop function anymore. Yeah, it probably doesn't. Oh, there's also this part that I forgot to mention. That this is a function that is passed here, which is this function here, and this is gonna run inside of the provider component. And it just sets the events. Which is also, the events I'm also struggling to understand because it's not very... Like, I don't understand why they create... It seems like they create other objects or like some functions to keep track of events and to like create a bridge between the 3JS rendering and the events. And I think that it has to do with the nature of the events. There's a difference between events inside of the 3JS because 3JS itself doesn't have any events, so the events have to be on the DOM, but then like I don't understand very well. In my mind, like all you have to do is put events on the canvas and then you do stuff based on that. So, but I remember on the article that I read from the guy that's works on React Fiber, that he explains some stuff about events, but I don't understand very well how it works. But I think it doesn't have anything to do with the loop, probably. Or maybe it's this one, set frame loop. So initializes, but I think this has to do with the use frame hook. Like it's not gonna call request animation frame. It just sets the thing. And it's just a string. I think this is used at some point in some of these functions to determine like how the loop is gonna run or something like that. I remember seeing this, but I don't understand very well how it works. Yeah, here is one part. There's nothing here that it seems like... I think this is probably was related to the issue I was having at some point, but I don't remember. And I don't understand why though I was having. I think maybe this active true has something to do. That the canvas is active, rendering will now begin. I think this is probably the part that initializes, and it has to do with the internal, which is the stuff that has the subscriber function. So I think probably this is the property of the star that initializes the rendering loop. So when it's set, it's probably right here that initializes. So I think I have to understand this one. Maybe it's on the star. Yeah, I think it's this object here. So active is false. There, this is the stuff that it doesn't make sense because it's not used here anywhere. Go right back. I'm gonna spend some time trying to understand this, and then after that I start studying the graphology stuff. I think I'm gonna try to spend 5 hours here today. Then hopefully, I think I'm gonna do it for when I hit 2 hours and a half. Then I'm gonna start studying compilers. I think probably what I'm gonna do is like I didn't want to. At this point, I wanted to have everything for the visualization set up, but obviously I don't have yet, so I'm gonna have to figure that out, I think, because it's very important. So I'm probably gonna go back and forth during these 2 weeks between the two. But I think I need to catch up on the compilers, and it's gonna be extremely difficult, I think. Like, I'm expecting to be very hard to parse the... Because this is the biggest problem. Like, the main thing that I'm trying to achieve is to create something that allows you to transform code into visualization in a way that makes it a lot faster to learn things. And I think that the way that I'm going to do this is through like a multifactor approach. But like the nuances of this and to actually do it is going to be extremely difficult, I think. And it's going to require me to understand like I'm going to focus only on one language first, which is going to be JavaScript, and then I'm going to focus on Python, I think, because it's just the easiest ones and the ones that most people use. And if I try to focus on too much, then I'm not going to do anything, I think. So I think the first one is going to be JavaScript. But then obviously I'm going to have to parse the code in another language or in using Node.js. So like I'm not going to be able to parse the code from the front end because the front end doesn't allow you to read files. So you need a backend. So the plan that I have now is to start, like in the beginning I thought I was gonna allow people to put code and then I would parse their code. But I think that this approach also adds a bunch of complexity. So I think it's much better to start like by creating something that I'm gonna parse like completely separate from the website, and then I'm just gonna create the graph from the parsing. And then from that graph, I put I create a folder on the project, and then I just create a page based on the folders that I have. And then after I set up things that way, and I optimize this process of taking the code and transforming into visualization, then I can think about allowing for custom input from people. I think that's the plan. There's a long way until I get to that point, I think. So I think this is the object this is the value that is responsible for handling the state of the loop, I think. And the subscribe is related to use frame because it's the thing that I talked about. It's gonna allow you to put functions that are gonna run on the thing. This probably holds the frame. The priority is probably the priority, like the name says, of the stuff that is gonna run. But like, at what point does it run things here? That's the thing. Because there is no like nothing related to request animation frame here, and this active value seems like it doesn't do anything here. Oh, maybe it's this one. Because it subscribes this in the beginning, when it creates the store. But how is the subscribe? Like, at what point are the subscribe? Maybe it's on the loop. The subscribes are called. So the values gets the state. Okay, so it's here. This is the part. So the loop is the one that creates the rendering. So I need to find at what point it's gonna call this function. So it sets as active there on the onCreated, which is gonna happen inside of the provider, which is the components here. So it's gonna happen here. And this is gonna set up the active here. And then based on this, there's gonna be a condition that is gonna allow the thing to run. And this is the loop. So this is the main function that handles the loop. The render probably contains the subscribers, I think. Yeah, this is the function that I think I saw the conditions. So I think I looked into this function, but I didn't, because I was just focused on all the other stuff. I didn't pay attention to this one. So here is gonna loop through the subscribers. And then it gets the state based on the star. It makes the graph based on the state. And then it calls the render from the GL. I think the GL is gonna contain, the GL is from the story and contains the 3 WebGL render that initialized in the beginning. And this function is gonna render the thing. So this is the part that it does the rendering. I don't understand really well the, like, how is it calling each function here? Like, why does calling the current from the graph is gonna call the function? I don't understand that. So it seems like it is looping over the subscribers, and this is the part that calls each function from the subscribers, the callback functions. But I don't understand, like, I don't know for sure if that's the case, and I don't understand if it is the case, how does it work? Oh, I guess it's because when it pushes the subscribers, it doesn't push only the callback. Now I remember, I think. So the first argument is a ref, but yeah, I think it's because of the way that the use frame is set up. I think I'm conflating things because I'm imagining that the first argument that the use frame is going to receive is the callback function, but I think that on the subscribers, the first argument is not the callback function. So that's what is confusing me, I think. Because he's gonna pass a ref and something else there, if I remember. Yeah, it passes a ref, priority, and star. So how is the subscribe related to the use frame? I think first I need to understand this part here. Then I think about the rest. Yeah, because here is calling root state subscribe, which is this one. Just calling this function. And then it does pass the function as the first argument. But here it says that that is a ref, so like how does the function becomes a use ref from React? I don't understand this. And then it pushes to the subscribers as an object. So that value is going to be an object here. This is going to be the object. The object has the ref, which is the first argument. So I guess the ref is just a function, and then it calls the function. But it should be a use ref, that's the problem. So, like, I don't understand how he passes a function here and then it becomes a ref here. Maybe, yeah. Because it's calling directly from the store. Unless there, maybe I'm confusing the issue because, yeah, it's calling the other subscribe. So there's probably a function here somewhere. What's that? Oh, it looks like it doesn't have any function. So oh, it is a callback, but so I guess it has to be this one, even though it's not calling internal first here. Because there isn't any subscribe here. Unless I'm missing something. Yeah, but whatever. So we're gonna assume that it's just a function. It's calling the function here. It's calling the function and passing the star. So the subscription star. Yeah, which is the star. This argument here. So the subscription is going to be this object. The ref is going to be the function, and then it passes the star as the first argument for the function, which is the star. And then it passes delta and frame. Delta, I think, is the time that it has passed since the previous frame. And frame is what frame it is. So the callback functions that are passed inside the use frame probably receive these three arguments as well: the star, the delta, and the frame. But maybe just this true, because the use frame might be different than this function here. Oh, but it looks like this one doesn't use any arguments, so. So I think this is just the initial setup for the camera and the viewport. And then it calls, also here it calls this invalidate. But at what point, I have to figure out at what point it calls the loop actually. Because I understand now, but the loop is not called anywhere there. This name is kind of confusing as well, I think. So maybe the invalidates is the first one that runs. I guess it's just confusing because of the name. Because like this leads me to believe that the function is supposed to invalidate the loop, not start the loop, I think. So I think this one is the one that starts probably. Validates the view. Requesting a frame to be rendered view globally. Oh, maybe this is when you manually want to change the request animation frame. It's very confusing. Also, here it does call this function. So maybe this is the one that initializes. So when it initializes the store, it calls this function with the state. And then it sets that to the store. Or it calls the subscribe and then passes the function. So it calls the subscribe, passes the function. This is the thing that is weird because it's just passing one argument. So, like in my mind, it should be the first. It should be the ref. This state here that is passing. But it makes more sense to be the star. This part is kind of hard to understand as well. Because like I don't understand like how is this gonna be used, at what point it's gonna be used. Obviously when you call there, it's gonna return this as a function, but then like is this gonna be the state of the store? It's weird because the first argument is a ref, and then like here is written as state, which makes me think that is the star state. I think it makes more sense to be the star state, but I don't know. I don't understand how this works. Also, it's the object. Yeah, which is the star state. So it's this object here. Which is the star. I think that at that point it probably starts the loop. I think that's what makes more sense, because it calls the request animation frame here, and then it passes this function, and this is the function that is gonna manage the subscribers. It has to be that, because there isn't any other parts that it calls anything related, I think. Yeah, I think at that part it doesn't start, it just sets up because of this. So at this point, because it was set up before, it changes the active to true and then makes the condition true, and then it calls the render function. Yeah, so I think I'm gonna go to the graph again. It is really fucking confusing, to be honest. Because the problem is I still don't get the... Like, obviously it's using a request animation frame there. So I think it's the whole stuff that I talked about with the browser. I think the point of this is just works as a callback, and like it's not gonna change anything in the source code of React Fiber. I think it's just setting up on the as a callback so that it runs asynchronous, and it just calls on the next frame, and that makes it so that the graph is built first. I think that's the... I'm gonna assume that's the reason why they put there. So here, the first time is gonna call this. I think this is the part that is gonna decide. And I think I already looked at this at some point, and it uses data. The data attribute on the nodes and edges, but I don't understand how it works. Because on this example that I have now, I'm using the same data structure that they use. The only thing that I changed is the color. Because the way that they were doing it, I think they were passing the color as props and putting that on the component, and then because they were using React Fiber, so that they pass as props and they put as props on the components from React Fiber. Just select the color. But the way that I'm doing now is putting on the nodes and edges directly, the objects. Because that way I can set up the colors and the sizes based on whatever I'm gonna do with the parsing of the code first. I also don't like the way that they do the labels here, so I'm gonna have to see if the reason why they do it like this is because of Graphology, but I don't think that's the case, hopefully. Because I think it makes a lot more sense to just put... and I'm gonna want to put other stuff as is strings here, to encode information. So the nodes on the examples also don't have any, like it's the same nodes, so like it shouldn't be, the problem shouldn't be an attribute of the nodes. It should be because of the React 3 Spring, I think, because they are using that library and I'm not using that. And so the type is going to be the type of the layout. This is probably the ones, yeah, it has to be the ones that are available. And then it's just going to match. So the function is always the same, just changes the stuff that it passes. And I think this is the function that is going to use a bunch of stuff from D3 to calculate everything, I think. This is something that I'm gonna have to think about as well. Like, the more that I think about it, the less necessary I think that it is Rapier, and it just adds a bunch of complexity, and it's kind of annoying to deal with the async because it uses was, and I think it's not very necessary. I think like the biggest thing about physics engine that is useful is the collision detection, which is very complicated to do. But I think for my use case, it's not that big of a deal. Like, as long as the dragging works, I can use the raycaster to separate the nodes, and because it's 3D, and I can allow people to customize the visualization. I think for what I'm doing is not very important to have collision, like an advanced collision detection. Like worst case, I can just do like as a square between the circles. Like instead of a circle, I put a square, and then just calculate the area of the square, and then I check to see if the nodes are on the same area. But then I would have to put some logic to determine like what's gonna happen. But you can simulate all the forces based on the positions, I think. But I think I'm gonna have to understand how D3 works, because I think it's gonna be very useful to have animations as well. Like, it would be really nice if you could simulate the execution of a script, for example. So, like, follow the script along with the graph, and that's gonna be very useful. And in order to do that, I think I need to... It's more the camera, but also the positions of the nodes, because it's obviously helpful if you can move nodes around based on the visualization. And this, yeah, it depends on the examples, I guess. Because it passes everything as a rest in the props. So I guess you can put an object and then it's gonna pass here, and then you can put those values there to customize. Maybe, I think that's not the problem. Like, if I change here, it's probably not gonna... I think the issue is something else with the... Yeah. Did I change something here? The controls are not working, so... That's probably because this. No, it shouldn't be because of this. Yeah, now the controls are not working for some reason. I don't think I changed anything. Maybe here? But it's... Oh, is the update. That's what I changed. Yeah, here. It's because it's not updating, so it fucks up. Yeah. I forgot about that. So let me go back here. Yeah, obviously it has to be something else that's is messing up the on my graph. So and so I have these properties, and then it's gonna call this function. So one of the arguments is the graph. And graph. Then it has the drags. Maybe it's the drags that is the difference. Because one thing that I did was to remove the use drag hook, which used use gesture to manipulate the nodes. So maybe that's the stuff that changes here. So just passing the IDs here to these ones. I'm pretty sure I have the functions, obviously. Otherwise, it wouldn't run. Force simulation. 3 forces. Yeah, no data here. But this should be... Maybe what I can do is just console log there as well. You go on the other project and I can console log. It could be this function, and it can also be the transform graph function. Maybe this transform graph. So the layout just creates the forces, and then the transform applies them, I think. But maybe... So one thing I can do is just see if I can console log here, I can console log on the other one, just see if it's gonna be a difference. And another annoying part about this one is that I can't open the developer tools. Maybe Control Y. See if I... Or Control Shift I opens. Because it's all on the canvas, so... And then there's the events on the canvas. Because it might be something because the other one's TypeScript and I converted to JavaScript, so I might fuck up because of this. This might be one of the reasons. It doesn't even call anything there. So I guess this function doesn't even run. I don't understand why though. Oh, so this one runs. It is because this thing doesn't return anything. Or it's because it's passing inside here. I think that's the reason. Because it's actually an argument of this function here. And because this function is from D3, then maybe it doesn't show there. Yeah, so here. So maybe if I just remove these things here. Because it should be returning something, obviously. But maybe this should work on JavaScript as well. Because it's just an operator from JavaScript. So that's not the problem. Also, it should be this cluster attribute probably. Yeah, maybe not. So I think neither of them it passes anything as cluster attributes. Oh, I think I changed this as well because it's TypeScript. I just didn't want to deal with the all TypeScript bullshit of figuring out all the types and all of this stuff as I was trying to refactor everything to make it work. There's just so much stuff to think about, and like it feels like this other stuff that just gets in the way. Yeah, so it is undefined here. But here, the other one doesn't even call this function. And that's what's weird. Maybe it's because this one is not calling. Yeah, but let me see here. So maybe something else related to the cycle. I think, yeah, that's the case. So the problem is that this is not even running this function. I think if it was running, it would probably be the same result because there isn't anything different on the nodes and edges. So it's probably something related to the request animation frame thing. I think I had a feeling about this. That's why I wanted to spend time there. So the biggest difference, obviously, is the way that I'm setting everything up. Because on one project is using the reactor fiber stuff, and in my project I'm using directly on 3JS. So that's the biggest difference. But I think here there isn't anything like directly correlated with reactor spring. Because it would have to be through the nodes, I think. And so I think I'm just gonna spend some time seeing if there's anything related to, that might be potentially related to the way that the nodes are rendered. But after console logging there and nothing showing up, then it's pretty obvious that the problem is that the other one is not running, but I don't know why. I think it could be either the cycle, or it could be the components, or the stores, or everything. Here there isn't anything that makes me think that like it's gonna be different. Maybe the drags. I think that the drags are the main thing. But I think that's not the problem. So another thing you can do is see here if it's gonna... I think it's not gonna allow me to do this, so... So it shows up undefined. Let's see here. So same thing. So it looks like it is calling this. So it should be calling the layout provider as well. Maybe it's just because of the type. Maybe it's because I'm not passing the correct way here. But I don't see why that would be the case. So let me just pass. Instead of passing here, I'm just gonna pass as an argument here. It looks like it doesn't change anything. And I think that the default props should work here. Because it is a part of the React. So why isn't it calling? So obviously I'm gonna console log here now. Yeah, it is calling here. Obviously, it's gonna be calling there as well. It should be because of the drags, I think. But why isn't the other ones? Maybe just I was looking at the wrong function because I had a different type there. I think that's the problem. So this probably, yeah, it is calling. I think that I was just looking at the wrong function because it's calling a different function. So I think that the problem is probably the drags here. I think that's the main difference between them. And it's coming from the rest. So on the other project, it's probably passing as a props. I think it's passing through the drag graph current. That's the main difference, I think. And drags is from the state. And the state's gonna be... This is gonna be related to the components, I think. Just an object. Yeah, I think I'm gonna take a break now. It's 2 hours and a half. And then I'm gonna start studying compilers and I'm gonna figure this out off stream. But now I think that like it's less bad because the problem is not on the related to the 3D. Like it could either be something related to the drags or something related to the nodes themselves, like the way that it works with the like there could be some functionality inside of these layout functions that would change the node somehow related to the D3 library. And I think that would make it harder, but I think if it's just the drags, maybe it's gonna be easier, I think, to fix this. So the main difference I think is that here is using the drags, which is gonna be a reference to the components on the DOM. So instead of making like that, I'm gonna have to figure out a way to create the link with the objects instead, with the graph objects for each node. And I think it's gonna be more simple than this, because then I don't need to involve React. You can just do something with the nodes themselves, and then just change the function based on that. So instead of just using the ref there, I use something else. Like instead of returning the get node position. But I have to understand how this function is used as well. That's the problem. Is it the only difference though? That's the... I think it has to be the only difference because the nodes are the same, the edges are the same, the objects. And the rest is just D3 functions here. So... Yeah, it has to be the drags is the only thing that is different in both cases. So this probably is used somewhere to change the nodes, the position of the nodes. So this returns the true functions, which is gonna be this. This returns the step and get node position. The step get node position. I think it's gonna call this step here at some point. And it also calls this one. So the layout is the step and node position, and then passes the callback, and also calls these ones here as well. Yeah, so here it calls layout that stuff. But the step doesn't have anything to do with the drag. It's just from the D3. And I guess it's just like any other one of those, which is just gonna call one step for the frame. But it doesn't use the get node position. And then the callback, so it's probably on the transform that it uses. And it sets the nodes and the edges here after he calls that. Yeah, here, layout, get node position. So that's the only difference, I think. Yeah, so what's doing probably is creating a ref for each component, and then it maps the ref with the ID, and then it just gets the node based on the ref. And then based on that position, it's gonna change the values here. So I think I already understood. So I know what I have to do. The only thing I have to do is just change the... I have to see how exactly does it map the drag graph with the nodes. Also, I don't even need the drag graph, I think. I can just get from the nodes directly. So, because each node, on the way that I did it, it has a position property after I create the graphics. So I think it's even more simple than it is here. I have the position through the mesh that I create on the node. I think it's gonna be really easy, actually. So these meshes here contain the position. So initialize as random. Then the node's a little bit up, the label. And then this position is gonna be just on the meshes. So I can access the graphics of each node here in the function instead. So I think it's gonna be a lot easier than I thought. And instead of returning the ref, it's gonna be even simpler than the way that they are doing, because they have to do it this way, because they're doing it with the components. And I have the nodes. And here, instead of mapping, I can... Oh, but it is already a map from the ID with the node, so... But I don't understand why does it return the node if it doesn't have the position. Because it should be just based on the position. Yeah, I don't get it. Because in the way that they did it... Oh, maybe it's here? No. Oh, they create the position on here. Yeah, but the way that they did it, the nodes shouldn't have a position attribute. But maybe they allow you to put the position on the node, and then it uses that position instead of the one from the reference. Maybe that's why. So I'm pretty sure that the problem is here, and it's gonna be easier than I thought to fix. Yeah, so I guess I'm gonna take a 15-minute break. I'm gonna remove the camera, and I think I'm just gonna eat something and then meditate. And I think I'm gonna start studying compilers based on this stuff here that I had for a long time, which is a super tiny compiler. And I'm probably gonna watch a bunch of videos that I have here as well. And I think next time, like, I'm gonna do the same way that I do everything else. You just like watch a bunch of videos and read a bunch of articles in the beginning, like get some surface level understanding and get some breadth of knowledge, like try to see a bunch of different opinions and like what are the relativistic symmetries that determine the way the compilers are gonna work. Maybe it's gonna be interesting to spend some time understanding like the whole feedback loop system there, and the stuff that I talked about a long time ago, not a long time ago, but a while ago, about how binaries become characters and why characters can't become binaries in the same way that binaries become characters because of the relationship between symbols. So I do want to clarify, like, how is it possible? For example, there are a lot of languages that the compiler is done in the same language that it compiles. So this is one of the things that I want to clarify a lot. And there's going to be relativistic symmetries that determine how the structure of compilers. And I think that's going to, like, the main difference between languages are the compilers and the interpreters. It's going to be very interesting to understand. And the main thing that I think I want to understand first is why different languages exist in the first place and what are the trade-offs that they are making. And so the first thing that I want to do is just read this stuff and like get a bunch of breadth of understanding, and then after that I'm gonna start trying to build stuff, and I think I'm gonna do it on Python first. So either Python or Node.js, but probably Python first, because parsing everything in Python is gonna allow me to do the Python one. Like the first one that I think I'm gonna do is for JavaScript. So I'm gonna create something in Python that parses files and extracts the information and puts the information on visualization. And it's gonna be parsing JavaScript code with Python. And then after that, I'm gonna move to parsing Python code with Python. And then I'm gonna create a funnel of information from like get the projects, parse them, and create visualization, and then find the patterns among all the projects simultaneously, and try to increase the efficiency in which I understand all the projects on GitHub. So that's the goal for now. So I'm gonna take a break. I'll be right back. I'm gonna put the timer when I come back. I think I'm gonna eat watching the videos first, then I'll meditate. So I'll be right back.
Let's create an interpreter for our own little language. An interpreter receives some code as input, and it reads and executes the instruction on each line one by one, effectively running the program on the fly. A popular interpreter you may know is the Python interpreter. Whenever you write Python space main.py, you ask Python to interpret and thus execute the main.py file. This is different from what you may know as a compiler, which also takes in code, but it then abstracts it, optimizes it, and lowers it to an intermediate language to then be translated to machine code. After compilation, the machine code can then be executed. Now that we know what an interpreter is and how it's different from a compiler, we need a language to interpret. The language we are going to create for our interpreter to read is a stack-based language, which means all its memory management is done on a so-called stack. A stack is just like an array, starting at index 0 and ending at index n-1. But unlike an array, we don't say things such as stack at index 3 is equal to 7, because a stack is a last in, first out data structure, relying on something called a stack pointer, which points at the top element of the stack, and two main operations, push and pop. As an example, we say push 10. This moves the stack pointer up one index and puts the 10 on that index. And if we want, we can repeat this with other numbers. The pop operation is the opposite. It returns the value that the stack pointer is pointing at, and then moves the stack pointer down one index, effectively forgetting that 7 is on the stack. Now that we know how a stack works, we know how a stack-based language like ours manages its memory. So let's take a look at our language and its instruction set. You are already familiar with the first two, which are push and pop. In the description of the push instruction, you can see that we receive an opcode, which is the word push, and a number, which was the number 10 or 7 in our previous example. Let's look at two other instructions, add and sub. Add and sub work similarly, that in both cases only the opcode is needed, because they both pop the first two numbers from the stack and either add or subtract them from each other and push the result back on the stack. We then have the print and read instructions, where print is given by the opcode followed by a string literal, and it outputs that string literal to the terminal. For the read instruction, we only expect the opcode, and this allows the user to input numbers into our program. Finally, to make our language a little more interesting, we want to introduce branching and loops, and we do so by introducing labels. And having these labels allows for two more interesting instructions, namely jump when equal to 0 and jump when greater than 0. For both these instructions, we expect the opcode and a label. If we use the jump when equal to 0 instruction, we check whether the top of the stack is equal to 0, and if it is so, we jump to that label, which is a position in the code. If it is not equal to 0, we continue to the next instruction. Let's take a look at two example programs to gain a better understanding of how our language works. Here we have a program which checks whether two numbers are equal. First, we ask two numbers from the user, then we use the sub instruction to subtract them from each other, and then we use the jump when equal to 0 instruction and the label L1 to check whether the top of the stack is now equal to 0. When it's not equal to 0, we jump to the next instruction and print not equal, and then halt to stop our program. If it is equal to 0, we jump to L1, print equal, and then halt to stop our program as well. Here we can see a more complicated program, which uses branching and labels in order to create a loop, and it does this in order to find out whether a given number is even or odd. The approach is as follows: read the user input and put it on the stack. If the user input is 0, jump to L1 and print that it's even. If not, push 2 to the stack and subtract the 2 from the user input until the number is either 0 or smaller than 0. If the number is still greater than 0, we jump to the loop label and repeat the process of pushing 2 and subtracting 2 from the user input. If the number is eventually no longer greater than 0, it must then either be 0 and thus be even, or it must be -1 and thus odd. Now that we got to know our language a little better by looking at these two example programs, let's add these two programs to a file so we can use them to test our interpreter later. To write our interpreter, we're going to use Python, which is quite funny because it itself is an interpreted language. So we're going to ask the Python interpreter to interpret our Python program, which is an interpreter which interprets our language. Let's get started writing the interpreter. When we run our interpreter, we're going to say interpret this file. So the first thing we do is we retrieve the program file path from the command line arguments. We then want to use that file path to read the lines of our program and parse it into a list of instructions, which we call program. We use a token counter which starts at 0, which we use to keep track of where we are in our program in terms of parsing, and we use the label tracker to keep track of which index in our program list a label is pointing to. For each line in the program code, we split it into parts and retrieve the opcode. If the opcode is an empty string, we continue to the next line because it is whitespace. If the opcode ends with a colon, we know it's a label. So using the label minus the colon as key, store the current token counter in our label tracker and continue to the next line. Otherwise, we append the opcode to our program list and increase our token counter by 1. There are several instructions which are followed by an argument. So let's go ahead and parse those into our program list. If the opcode we encountered was push, we know that the next part on the line is our number. We can append that number to our program and increment our token counter. If the opcode is print, we expect a string literal. And because a string literal might contain spaces, it might have been split. So to extract the original string literal, we join the remaining parts with a space and remove the quotation marks. If the opcode is jump when equal to 0, we extract the label from the line parts and append the label to our program and increase our token counter. And we do the same when the opcode is jump when greater than 0. Let's now see where we are at and print the program we parse. To run our interpreter, we write Python interpreter.py program1.ol, which stands for our little language. Running this shows a list on screen containing all the program instructions which should be executed in order. In order to execute the instructions, we are going to need our stack to manage the program's memory. So let's create a class called stack, which has a constructor which takes in a size. The constructor then creates an array of that size, filling all the values with 0, and initializing a stack pointer which points to index -1. We create a function push which takes in a number, increments the stack pointer, and inserts the number wherever the stack pointer is pointing. We also implement the pop function which stores the number at the top of the stack, decrements the stack pointer, and returns the number that was at the top of the stack. Finally, we introduce an additional helper function which we call top, which doesn't take any arguments and simply returns the top value of the stack without moving the stack pointer. Now that we create a class defining the stack and all the operations we can do on it, let's initialize a stack of size 256, and we also initialize the program counter to 0, which is the index of the instruction we are currently at in our program list. Now that we've initialized a specific stack and we have our program counter pointing at the instruction that we need to execute, we say that we want to keep running the program as long as we don't encounter the halt instruction. So while that is not the case, we read the extracted instruction opcode and increase the program counter, and then we have an if statement for handling each opcode. For the push instruction, we take the number that the program counter is pointing at, increment the program counter, and push the extracted number to the stack. For the pop instruction, we simply call stack.pop. For the add instruction, we pop two numbers from the stack and push their sum. For the sub instruction, we also pop two numbers from the stack and push the result of subtracting the first number from the second number. If the instruction is print, we read the string literal at the program counter, increment the program counter, and print the string literal to the terminal. If the instruction is read, we read a number as input from the user and push that number to the stack. If the instruction is jump when equal to 0, we store the value at the top of the stack. If that value is equal to 0, we set the program counter equal to wherever the label tracker says that the label is pointing. Otherwise, we increment the program counter to move to the next instruction. Finally, when we encounter the jump when greater than 0 instruction, we store the number at the top of the stack, and if it's greater than 0, we set the program counter equal to wherever the label tracker says that the label is pointing. Else, if the top of the stack is not greater than 0, we increment the program counter by 1 to move to the next instruction. Awesome, we've now dealt with interpreting all the instructions that exist in our language. So let's run our custom interpreter on our little language files. We say Python interpreter.py program1.ol. This runs the program expecting us to enter two values. We can enter 1 and 2 to see that they're not equal. We can enter 3 and 3 to see that they are equal. Let's interpret and run our next little language program. It expects one number from the user, and when we enter 7, we see that the program recognizes that the number is odd. When we enter 232, we see that the program recognizes that the number is even. And this is awesome because this means that both our language and our interpreter work. We're able to use labels to successfully branch and loop in our little language. I hope you learned something new in this video and had fun learning how to create a new language and interpreter for that language. If you did, please leave a like. If you want to see more content like this or see me expanding the language and interpreter, consider subscribing. Have a nice day. Peace.
Hello everybody, welcome to the Language and Translator class that's being given at the UCL, the Université Catholique de Louvain, and is also being uploaded online for everybody interested in compilers. So this is about compilers. A compiler is the program that
In this series of learning programming in C, today I am going to talk about language translators. In the previous videos, I have already discussed like what is need of programming, why do you write programs, what is need of programming languages, what are low-level programming languages, high-level languages, right? Now see, in this video we are going to discuss language translators. Now, why do we need language translators? What are language translators? See, language of computer is a binary language. Computer can only understand zeros and ones. So if you write code in machine language, that is okay. That is zeros and ones form. So computer can directly execute that program. But if you write programming assembly language or high-level language like C, C++, Java, C Sharp, JavaScript, then those programs have to be converted into object code. Object code means machine code, zeros and ones, because computer cannot understand assembly language or that high-level language. Because generally we write programming English language. English means in assembly language we use what mnemonics. Like for addition we write add, for subtraction we write SUB. But computer cannot understand these words, these mnemonics. So you have to convert those mnemonics into machine code, into zeros and ones. And that's exactly language translators do, right? So we are going to discuss all the types of language translators in this video. Now let's discuss language translators. Three translators are there. First is assembler, compiler, interpreter. Assembler is what it is basically used to convert the program written in assembly language into machine code or object code. Assembler is specifically to convert a program which is written in assembly language, right? And machine code means zeros and ones. So you can say assembler is a computer program which is going to convert the program written in assembly language into machine code or object code, right? Next comes to for high level language, for converting high level language into machine code, two translators are there, compiler and interpreter. So let's see the difference between these two. See, you must have heard of compiler, and you're using compiler also. When you're writing program in C language, you compile that program, then you run that program, and you get output, right? So now let's see the difference. Both are used what to convert high level language program into machine code. Machine code means zeros and ones form. See, both will convert high level language program into machine code. So what is the difference? Compiler converts it before the execution of the program, and interpreter converts while the program is executing, while the program is running. Now what does that mean? See, suppose you have written a program in C language, right? Then suppose this is a program, you have written this program, and the suppose name is what? First dot C. Compiler will take this program, complete one, all the statements written in this program, right? Maybe 10, 100 statements, how many statements? All the statements it will take and convert it into object code. Machine code, zeros and ones, right? And after that, linking is done, loading is done, means after that executable file will be created, and then you run that executable file and then you will get output. That was what we discussed. See, compiler will work on which model? Translation, linking, loading. Three steps are there. Translation, linking, and loading. That we will discuss next video, the complete process, right? But interpreter act upon interpretation mode. Now what does that mean? See, same program I'm going to take, and what interpreter will do? Interpreter will take one statement, line by line. It's not going to take the complete code as compiler do. It takes first line, first of all, right? Change it into some intermediate code, and or you can say object code, and at the same time give you output. At the same time, you will run the statement. You can say in simple words. If you run the statement, convert it, then run it. Statement by statement, right? So while converting, interpreter also takes the data. If it is required, it is required for the program. And in this case, it's not like that here only you will get data. No, first the program will convert to object code, exe file. After that, data will be taken to that exe file, and then the program runs. But here it takes line by line. One line, interpret that line, convert it to object code, and run it. After that, second line, convert it to object code, and run it. Means what? It will convert the code high level language code into object code while the program is running. Means execution of the program and the conversion and the translation was parallel. But here translations are done before the execution. It's not a parallel process. That is the main difference. So now what is so it is not going to do some linking and loading, but like we do translation as well as linking and loading. Fine. So now what are some memories and brackets of this thing? I hope you know the process, how compiler works, how interpreter works. See, directly we get output, no object code. So one more difference is what? Here object code will be created, here no object code, no separate file will be created for object code. Next difference is what? It is slow. Why so? Because it is executing line by line. It takes one line, interpret it, means convert it to object code, and then run it. Then again it's second line, then CPU will wait. Right? Then convert it into object code, then run it. But the time taken by the compiled program, see, compile the complete code at one time, right? And then when it's going to execute, time to execute that compiled code is very less. Then the time to interpret is slower. Since it runs slower than the compiled code. And next difference is what? See, when you get errors after compiling the complete code at last, here you will get list of errors, or warnings and line numbers. I hope you have this thing. But here when you get errors while running, see, it is taking one line by line, statement by statement, and then converting it into object code and then running. But if any error then first line, then it will stop here. At the same time, it will show error. And so debugging is easy in this case. Finding out errors is easy. But here it is tough because first it will give you list of errors after compiling the complete program. Then it will give you errors. So debugging is you can say comparatively tougher than this one. Here in compiler. See, here it's not like that object code will be created. Means you rather say if there is no error in your program, then only it will be successfully compiled and then only it will be object code. If error comes, then you will have to get back to your source code. You will have to correct those errors. Compiler is not going to correct errors. It is only show errors. You will try to modify the program again, save it again, compile it, and if there is no error, then only it will object file. And then the program then run. Right? And next is what? Once successfully compiled the program, once object code has been created, then after linking and loading executable file will be created. After that, to run that file, there is no need of this source code. You can directly run that executable file again and again with different output, different inputs and obviously output, output, output. No need of the source code. But here you will need source code. Why so? Because here it takes one line only, line by line, statement by statement. It sends the program statement by statement at one time. It takes one statement at one time. So to make this line, interpret it means convert it into object code and run it. Then again to run the second statement, obviously interpreter needs the source code, right? So every time it needs source code to run the program. Next is what? It generates intermediate code, object code, so it needs more memory to store the source. But here no intermediate code, no object code, separate file for object code has been created, so it requires less memory. Right? It directly executes the program. You can take an example to see the working of this thing. See, suppose in Russian relation to a Russian language like so and they speak Russian language, they don't speak English. So a Russian understand Russian. So he needs what? A translator. Whenever they speak like one language Russian language, the translator will convert that into Hindi, into English. Again, he speaks second line and the translator will convert it into Hindi or English. Right? And then a PM will understand. And when a PM speaks English, they will understand because their language is Russian. So their translator will convert whatever a PM say line by line to Russian language. So that is what it's kind of interpreter, like line by line. But second case is what? It's what they are watching Russian movie. So they have done that movie, they have given those subtitles in English language. So whenever you watch that movie, every time no need of conversion from Russian to English because you have already compiled that language, compiled that movie. You already subtitles, that English subtitles. So whenever you watch, you will get those subtitles. No need to convert that movie again line by line. Fine. So that is what you can say example of compiler. I hope you can relate these things. Fine. So next is what? The language which is interpreted languages are Python, Ruby, Perl, and compiled languages are what? C, C++, C Sharp, these kind of languages. Right. So if you want to know these compiled languages in this directly component, what? Then write source code, compiler, then object code, or you can say machine code, and then you get output. I'm writing this source code, this is output, this is machine code. And here this is what? Source code, interpreter, and directly you get output. No object code and machine code will be generated in a separate file. Right. And here as I have told you, there's no compiler, there's no source code once that object file has been created. Right. And then and then separately that executable file. So no need of this compiler to be present in memory while executing while running that program. But here while executing the program, interpreter needs to be in memory. Why so? Because it takes line by line. The version and the running of the program is parallel here. So it needs to be present in memory at that time. But no need of this compiler in memory while executing the program. Right. So I think these are the differences between this compiler and interpreter. I hope you got my point. So that's what this video. Next video we'll see that translation, linking, and loading process. How programs when you execute program and how that program gets executed. We'll see the complete process. So that's the next video.
that implements the programming languages. It takes you from the source code, which is just text, into an executable that can be run. Or in some cases, it goes from the source code, it's being fed into an existing program that executes the program. So we'll learn all about how programming languages execute in practice and how we can write this program that compiles or executes source code. Before we get into the thick of it, I want to debunk two misconceptions about compilers. So the first one is that you might be thinking, well, I program mostly in JavaScript, Python, Ruby, whatever. I don't need a compiler. I'm just running my program and I don't need to compile it beforehand. It's true, you don't need to compile it beforehand, but when you run your program, there is a separate program called typically a virtual machine or an interpreter that does compile the source code on the fly. So most of what we're going to say in this course is going to be applicable to these dynamic languages as well. The second misconception is that this is a class that will touch on programming languages, paradigms, and concepts, things like functional programming, etc. This is not the case, despite the title of the course is Languages and Translators. This is about implementing languages, and we're going to stay fairly general. Of course, there's a lot of synergy between programming language features and compilers. And I hope that by understanding the implementation of programming languages, you'll be able to understand better why features are a certain way and how they can be implemented. Also, if you do the project for the course, in which you will have to implement your own programming language, then you'll be free to experiment with whatever feature you can think of and how they will be implemented in your language. All right, I haven't introduced myself. So I'm Nicolas, and why am I here giving this course to you? So I did my PhD at UCL, and I completed that in 2019. And that PhD was in parsing. So parsing is a part of a compiler, typically, but also used outside of compilers. And it's the process of going from text, for instance, source code, into structured representation. We'll learn all about parsing in this course. It will be one of the first things that we tackle. Since my PhD was completed, I've moved on to work on a Ruby implementation called Graphology, and that work is being done at Oracle. So you may know Oracle for their databases, and you also know them because they're the steward of the Java language. So Graphology is an implementation of Ruby that runs on the Java virtual machine, but that also uses state-of-the-art compiler technologies, notably RALVM and Truffle. So I'm not going to give you any details right now, but towards the end of the course, we'll speak more about Truffle and RAL, because they're a very cool technology which I think will factor into the future of programming language implementation. To help me in this course, I have the help of these two handsome young men, Mathieu Jardin and Alexandre Debray. They will be in charge of the lab sessions, in which you will learn to use tools that you will need in projects to implement your language, and they'll also be in charge of the project itself. For the rest of this video, I want to give you some motivation for following this course. I think it's important to know why we're learning about what we're going to learn about, and in general, why we're doing things, and to make sure we're not wasting time. So obviously, you're going to learn about compilers and how to write them. This might or might not interest you. Maybe you say I don't want to write a programming language. People than that can use what they did, and that's true. But a compiler is a tool that all of you are going to use on a daily basis if you work at a programmer role, even if you work in IT in general. And I think it's good to understand your tools in a deep way. And like I said, understanding how the compiler works will help you understand language and use language more effectively. Even if you're not interested about writing compilers, there are parts of compilers that actually have their places in other projects, and more particularly parsing, which is going from text to a structured representation. If you have configuration files that you need to parse to extract all the configurations that you manipulate in your program, well, that's parsing. I'm pretty sure all of you have dealt with parsing extensively, no matter your experience, because it's such a big part of programming and computer engineering in general. Typically, you delegate that to a library that does it for you, but you will learn how to write your own parser in this course, and also you will learn to understand how these libraries work themselves. So something useful is that understanding compilers will help you understand your programming language better. It will help you understand design decision in these languages, and also why they may have some limitations that you never really understood. And also why sometimes it's possible to do better. Sometimes languages have limitations that there's no theoretical basis. They should have that limitation, right? So I hope it also motivates you to write your languages that don't have these limitations. And the third thing that you're going to learn in this course is some useful programming patterns that you can use in things that have absolutely nothing to do with compilers. The first is domain-specific language. So typically when you write a program in programming language, you are writing a computation. Okay, you're writing something in language. With domain-specific language, you're using language to write a description. And this description, then later you're going to use this description. There's data structure that describes it could be a configuration, it could describe some a data pipeline, something like that. And then later you use the description and you're going to interpret it. Right, so first you define it as a domain-specific language, and you write a description of it, and then later you interpret it. And typically the data structure that we're going to use to represent this description are trees. And we're going to talk about that because it turns out trees are very central to compilers. It's going to be the data structure that we operate on most of the time. Sometimes we're going to deal with graphs, but mostly at the core of what we're using trees. And it turns out also domain-specific language can be very useful in writing a compiler. So we're going to use these techniques to write compilers. And I hope you can then apply them in other domains. So okay, I told you that my course was awesome and it's going to be interesting. Generally, people find compilers interesting, so here are some comments I found online that go in that direction. For what it's worth, parsing and lexical analysis was the CS class I've used the most thoroughly in my career. Sure, data structure is probably the most I've used, but other than tables and B trees, not much of that class was useful. But lexing and parsing seems like every other project benefited by either handling configuration styles or log sensor data or some other need to convert what was human readable into machine manipulable. So this was a comment on Hacker News. Having written a compiler is definitely one of those, if not the most important things that upgrades a programmer. Bonus points if you can write a lexer parser and we can Walter. So this was a Reddit comment, and the topic of the Reddit post was an article written by Walter Wright, which is the creator of the deep programming language. I think it was an article on parsing actually. So then there's another answer. It says, definitely, you learn so many transferable skills in writing a compiler. I think everyone should do at least once. So I hope these people are right and that will come out of this course having learned a lot. And well, you will do it at least once if you do projects and projects in language. That's it for this video. Next time I will walk you through the compilation pipeline. So basically all the stages we need to go through in a compiler, and this will serve as an overview for the course as there'll be different lectures that go over all these stages. Take care and see you next time. Hello everybody. Today we're going to talk about the compiler pipeline, so I'm going to walk you through every stage of a standard compiler. So this is what it looks like. We have lexing, parsing, synchronization, optimization, and then code generation. Let's start at the beginning. So lexing. Lexing is about going from the text input, your source code, basically when you're dealing with programming languages, to a list of tokens. You can think of tokens as a word. So what's the source text from the perspective of the computer? It's just a bunch of letters, characters really, one after the other. It doesn't really mean anything. And the first step into extract meaning from the source text is going to be to chunk it in words that have meaning. So if you take an example here, you see that I've chunked the text of simply characters. But really the unit of meaning here is that we want to recognize that foo is a variable, equal and plus operators, bars are variable, for each is a number, so that's how it should be chunked. So nothing really mysterious here. You just go to text, from text to tokens. The next step is related, so parsing. In parsing, you take as input your tokens that you have, but you don't think of them as a list of tokens, right? You don't think of it as food and equal and bar and plus. You think of it as, well, I want to add 42 and bar, and I want to take the result of this addition and put it into foo. So what you really want, ultimately, is a tree like the one we have here, which gives you the hierarchy of operation, right? You have the addition on the one hand, and the variable on the other hand, and then you want to add them to one another. This whole tree is called an abstract syntax tree, or AST. Now we'll see later why it's called that way, but you can see it as a tree, you can see that it deals with syntax, and the abstract part just means it doesn't have to follow the structure of a program. So that might be a bit mysterious, but we'll see in follow-up lectures what that means. So yes, the first thing actually the parser does is extract the structure. Oops, sorry about that. It's not actually the only thing that it does. It also does another thing, which is it catches syntax errors. So I put you two small program fragments here. The first one is syntax error because it's missing parentheses that you should have here in Java. That's a syntax error. This is also an error because y here is not defined in the program. That's a syntax error. The parser cannot catch this. So moving on. Yes, so something important to say is that lexing is optional. It's supposed to be parsing without lexing. That's called a scannerless parser. And also, people often refer as parsing to actually lexing and parsing both. So sometimes distinctions are made. Let's move to semantic analysis. Semantic analysis is a series of checks that you perform on your abstract syntax tree once you have it. The two main types of checks you'll do are name binding and type checking, and then you'll do some other stuff as well. So type checking, as you might imagine, is verifying that the types used in programs are in accordance with the values that are being used. So if I define here a function called print that takes a string as a parameter, when I call the function, it has to be a string, not an integer, otherwise it's type error. So that's very obvious. Type checking is also concerned with the question of type inferencing. So if I define a variable x and I assign that to foobar, what's the type of x? It's string, of course. And if I assign to y the result of my function, well, the result of that depends on the original type of my function. But to know the type of these variables here, I have to know the type of the right hand side. So that's what's called type inference. But actually, there isn't really a difference between type inference and type checking. Because even if you specify the type on the left hand side here, you still need to independently infer the type on the right and then check that it's the same thing. So really, saying this here doesn't let the compiler do any less work. Actually, has to do more work because not only does it have to figure out what's the type of the thing on the right, but he also has to compare that to the actual type. So there's one step in this small example that's not quite clear. If I want to know the type of y here, then I need to know the return type of my function, which is to say I need to know what my function is. And this, knowing what my function refers to, is the purpose of name binding. So I put a small example here. We have a class called whatever, which is a function. The function McGuffin assigns y to the result of my function like we did before, and then we'll just return some comparison here. And my function takes an argument and returns it. So the first thing we have to do is actually to look up my function. You can actually see that it's defined here, right? And because this function returns int, then we know that the variable y is type int. Then we can do the check here. Comparing integer with integer is obviously allowed. The type of this whole thing is a boolean, which matches the type of the return function, so we're happy. Another check that happens in here is that we check that 42 is indeed an integer. So this whole program type check, we're very happy. So name binding and type checking are really complementary, right? You can really do one without the other. And this example is very simple, but if you start having something like classes and inheritance, then it becomes much more complex. So something that would also do some other checks. One example is checking flow of your program. So here we define a function that returns int. We need to make sure that whatever program does, it ends up returning an integer. So you can see the if statement here, and the else branch does not have a return. So that's obviously an error that we need to catch. Another example would be if you take a programming language like Java that has access control. So you can say that function or class are public, private, etc. You need to verify that private functions or data is not being accessed. So that's another thing you can do in something like this. So moving on, we should normally talk about optimization. But this point is important to remark is that this pipeline is just one possible compiler pipeline. It's in fact a pipeline that would be used for an old school C compiler. So you do semantic analysis, and you get a tree. And then you're going to run some optimizations in that tree. And once you're done with that, you can generate code that tree for C compiler will be machine code. So that's one possibility, but there are many other possibilities. For instance, some more modern C compiler would perhaps do some optimization. Yes. Oops. This is bound to happen a lot. Like I haven't figured out the team bindings already. So you have your tree, and you might do some optimization directly in that tree, but then you generate some machine code, and you'll perform optimization directly on machine code. Okay. Give me a second because I've broken my setup. Looks like we're back in business. I was saying that you run some optimization in the tree, then you generate machine code, and you will run optimization in machine code. Now, an example of this architecture is, like I said, some more recent C compilers, in particular, those that use LVM. LVM is the low-level virtual machine. This is a very, very bad name because LVM is not, in fact, a virtual machine. I don't know why they call it that way. That's just wrong, so just don't think of it as a virtual machine. We shall see what a virtual machine actually is in a minute or so. And what LVM does that it generates something called IR, intermediate representation, and it runs the optimization on the IR. And then at the end, it generates machine code for the actual machine. So that doesn't mean used C compiler, but also other kinds of compiler that targets machine code. So Rust, for instance, would work with LVM. I don't know if it does actually, but it could. So let's take another possible architecture. So in this case, after we have a tree, and we verify something like this, we generate bytecode. So I call this bytecode. What I mean by this is some kind of machine code that's not going to be executed by a machine, but instead going to be executed by a virtual machine or is going to be transformed. So actually, it's called the LVM IR, the intermediate representation. It's called bytecode as well. And basically, every language has its own name for that. So in LVM's IR, in C#, it's called intermediate language (IL), and bytecode is a Java term. This course we're going to use we're going to learn about Java code, so I like to use the term bytecode, but if you use other terms, that's fine too. So in this example, we generate bytecode directly from the tree, and then we feed that to a just-in-time compiler. What is a just-in-time compiler? Well, actually, see there's a big divide here, the big wall. All of this on the left happens when you compile the program. Before you run it. And everything on the right, all these things, that happens when you run the program. So the compiler is just in time because you compile the program as you're running it. So it's just in time because literally before running it, you're compiling the program. And as part of that, you perform some optimization in the code. So this is what C# does. So C#, when you compile a program in C#, you get an exit file, but it's actually very deceiving because this exit file actually contains bytecode or intermediate language, which is then at runtime compiled to actual machine code for your machine. You can make it even more complicated. And this is actually what most languages of virtual machine do, like Java, JavaScript, just really ultimately shortly. So basically, you see that it's exactly the same as for C#. So everything to the left here, all of these is done at compile time. And at runtime, this time we go into a virtual machine. What's a virtual machine? A virtual machine is a machine that runs bytecode. Basically, so it runs something that looks like machine code, but it's not actually machine code because it's not an actual machine. It runs a virtual machine. And it's a virtual machine with a just-in-time compiler. So when this executes code, the virtual machine that shows, it can either interpret the code, which means that it will run it. It will run bytecode as though it was a machine code, but it will not generate actual machine code. Or it can convert it to actual machine code in a code generation step. Now, like why would it do this? Why would it ever choose to interpret the code when, of course, machine code is much faster? Well, there's a good reason. If it does this, it can collect profile information, so it can see what's actually happening when it runs the program. And based on this reported information, it can optimize the code better. If you ever claim that Java can be faster than C in some program, this is where it comes from runtime profiling of the code that enables better optimizations. This is pretty much the state of the art of optimization compilers, should say. And it's a very popular way to do it. So the Java virtual machine does this, the V8 JavaScript compiler. So that's what you get in the V8 virtual machine. That's what you get in Chrome and in Node.js. Truffle, sorry, that's the language I'm working on. Truffle is a bit more complicated because it runs on the JVM, but then there's a framework called Truffle on top of that. And the compiler has been modified to develop VMs, so it's a bit difficult, but the idea is the same. And if you use the PyPy implementation of Python, this also can architecture to get there. Of course, you make it difficult, you want to make it more simpler. Like who says you want to do an implementation at all, right? And we can distinguish basically two types of simple architecture. The very simple one is just interpret the tree directly. Don't do any bytecode that interpret the machine, just take the tree and visit that with a tree walk interpreter. Language doesn't do this because it's very slow, but Ruby uses that for version all the time. So that's the proof that even doing something as efficient as this is not preclude your language being successful. The other thing that language will do that's a bit more common is to actually generate bytecode and then run it in a virtual machine. So that's what the C Python does, as the standard implementation of Python, and also the standard implementation of Ruby, which is called YARV, yet another Ruby VM. So I've molded the tree walk interpreter because I'm talking about this right now. In the project, this is actually what we'll ask you to do in the first time because it's much simpler than generating bytecode or things like that. And at least it will ensure that you have something that runs. And actually, it is an interesting learning experience to write tree walk interpreters. So what are tree walk interpreters? So I gave you a small example program right here, which is composed of two statements. So just do some math assigned to a variable and print variable. And then I've transcribed EST here. So our program, with the assignment, variable foo, we need to look it up to see what it refers to. We have our addition, nothing difficult here. For the poll, we need to look at print, and then we need to look at foo, actually the poll. Also, print as a functional language also has an EST for its body, right? I haven't presented it, but we need to know that it exists. Okay, so for the variables lookup that we have to do, these lookups are done in something called a scope. We know what a scope is, but here to make it simple, let's just make a single scope that's foo and print. So foo is a variable, so it refers to some storage memory, print a function, so it refers to the definition of function with its EST that we can represent. So actually executing this, how does it proceed? So it proceeds in a recursive way. So we start program, we're going to execute the assignment, we're going to look up foo, so we get the store, then we're going to do additions, but we evaluate the numbers, we add them up, and then we store the result in the store. Then we do a call for that implementation, we look at foo, since we store the element here, 94, we evaluate 94, and then we do the call, and actually this is just evaluating the EST here. And in the scope, actually, when we're evaluating here, there's going to be a parameter that's the recursive value here. So that's an overview of the tree walk interpreter, hopefully it helps you understand how that works. And then we get to code generation. So 2D machine code generation, bytecode generation is not making much difference. I have much to say about this, but for flavor, I want to give you a small example. So I have here a simple storing function in C, and here is the x64 assembler that's being generated for the function. So basically it stores the stack pointer here, the num parameter is being stored in the EDI register, then it pushes that on the stack. This is a stack address, then it takes that stack address, well, it takes the value of stack address in each register, it multiplies the register by itself here, and that's pretty much it. Basically the value return is one that is in the EAX register. This is a lot of super efficient. This is what you get when you compile the definition. If you compile the definition, you get the thing right, which is so reasonable. So like I said, EDI as the number parameter, just do that in EX, and then multiply EX by EDI, the result stored in EX and return. That's it. You obviously need to know machine coding source, that's the point of the course. That's just interesting stuff. Oh, and this is a multi-different source type, global.org. This is what you can play with sample C programs. You can see the machine code generated from different compilers, different transition levels. So if you're interested in that, definitely check it out. The second example is the same program, this time in Java, so we prefer to save that in the class. And we generate this whole pair right, and look at that because you can this class, it actually has a function, which is the constructor of the class that implicit. It records line numbers and stuff like this. But actually, what interests us is this part right here, that's the definition of the function. And so the x64 assembler we just saw is register-based, the machine code is register-based. If you know what register is, I probably should explain, but it's like the fastest level of memory on a computer. Now the Java code on the other hand is stack-based, so there's no notion of registers, everything's pushed and popped from the stack. And basically, what this ILO one here does is take the first parameter and push it in the stack. And then this IMO here says take the first two values in the stack and multiply them, push the result in the stack, and then we return. So interesting that it's a different way to work. Yeah, we will learn more about Java code towards the end of the course, and there will be an option if you want to compile your language to Java code. So finally, we come back to optimizations. We're not going to be very thorough on optimizations, but I want to give you a sense of what most common optimizations are. So you can optimize on the tree or on the target code or implement optimizations that are most of it. There are two types of optimizations that are going to be your bread and butter. They're going to drive most of the gains that you get. And these are first in line. So in line is just taking the definition of a function and putting it in another that calls it. So you replace function call by function definition. And the second one is partial evaluation, which is propagating information in the most famous member of the family of optimizations. It's called constant folding, where you propagate the value of constant flow. There's a few other things that we can roll, but I don't want to talk about them right now. I'm going to give an example in any partial evaluation though. So we have this simple program. We have this variable, so false. This function with condition either returns something ongoing or we call p with parameter true and get one, and itself if the boolean is var return for 2, otherwise returns 52. So we're going to be optimizing the function a. And what you could do is that we could inline. Okay, we could inline something ongoing and we could inline b. The problem is if we do this, and if we don't actually enter the first condition here, then this would be bad for cache locality. So I'm not going to details today, but basically, if you've seen in computer architecture or something how cache work, if you put a whole lot of code here and then foo is false and you jump to the code that matches this, you're going to incur cache miss, and so it will take time to retrieve the code basically. What we can do, however, is that we know that foo is always false, okay? So knowing that, we can actually get rid of this condition because we know it's never going to enter foo is false. Now, once we've done that, now we can inline b, right? So actually, that's what we do on the right, we take this definition here, and we put it here, and replace bar by the parameter true. Having done this, now we can actually constant fold true, because this is always true, right? And so it's going to be 42, right? This is here on the right, and then we're left with just 40 plus 1, and it's going to be 43. So we can go from this whole mess here to just return 43. And what's interesting to note is that there's really like a complementarity between inlining and constant folding and partial evaluation, right? Like if we just inline here, that might have been detrimental performance actually. But once we eliminate the if, then it's no brainer to inline b. And also, in b, say we optimize b, we couldn't have done anything because we don't know if bar is going to be true or not. But what happens is that when you pull this into a, you replace bar by its actual value, which is true. And so now you can optimize the value of b, which you could not have done if you did not inline it. So basically, inlining is super important because it enables new optimizations. And sometimes like a cascade effect where you inline something that allows you to do some partial evaluation, so you need some regression stuff, and then that makes it easier to inline more things, etc. So that's why I said these are bread and butter optimizations. And I think that's it for today. Yes. See you next time. We're going to talk about formal grammars and next thing, so we're going to get deeper into parsing. Take care and see you next time. Hello friends. So today we're taking a deep dive into parsing, and for that I introduce you to a very important concept called grammars. Remember last time we talked about the compiler pipeline, so there's a very simple classical pipeline. It can of course get more complicated with virtual machine and just compilers. Parsing though is going to be pretty much the same for any scenario. It's going to be a big part of what we focus on in this course. So you'll remember from last time that lexing or tokenization is going from input, which is basically just an array of characters, into an array of tokens, which are the minimum non-visible unit. Parsing, on the other hand, is going from these tokens into a syntax tree that gives meaning. So instead of just a sequence of units, it becomes a tree that gives meaning. You have the example of assignment that we saw last time. I'm here. Okay, so let me give some definitions. A grammar is the formal definition of a language. Formal here means mathematical, means it's precise. It's not like when you're going to describe a language to your pal here, just to be precise so it can be interpreted by a computer. What's a language then? A language is a potentially infinite set of sentences. So it's a set here in mathematical sense. What is a sentence? Well, a sentence is going to be conversely anything that's in a language. So if you take a programming language, a sentence is going to be typically a source file. Or if you have a read level print loop, it's going to be an expression that you can type in there and it can be parsed. That's one thing. If you go into language theory, there's a notion of alphabet, and that's basically just the set of tokens that we have in your language. Something I didn't say in the last slide as well is that sometimes parsing and lexing are done together as a single big parsing step, so lexing is optional. Okay, so we're going to focus on this example for most of our introduction parsing, and the example will be the grammar of JSON. So JSON is the JavaScript object notation, is a very popular format to store data and configurations. So what's the grammar of JSON? So basically, what you will parse, you can parse a JSON value. Okay, a JSON value can be a string literal. So version here is a string literal. It can be a number, 17. It can be an object. So an object is a series of pairs that are going to be bracketed by braces. So you can see all of these lines here, object, and the whole thing here is an object too. So we have a syntax for pairs, right? So that's here. You can see that these objects have a single pair, and the big object has two pair, one here and one here. And finally, an array. So bundle, the value of bundles here is the array that contains all small objects. This is a simplified grammar, so the real JSON also has like null, true, false. I think that's all I left off here. So it's almost the real thing. Another thing that's not represented here is the syntax of tokens. So I've highlighted here in red everything that pertains to the lexical part. And we'll talk in length about lexing a bit later. But for now, we're focusing on parsing to assume that we can recognize these tokens. So they're given to us, we just work with tokens, we don't do lexing now. Okay, so in this grammar, you see that we have a series of definitions. The things on the left, I think, are defined called non-terminals, while the tokens are being called terminals. So these are terms from the formal theory of languages. You can see how these terms make sense, right? A non-terminal is something that's a definition, a terminal is something that is given, it has no definition. And we'll expand on these terms when we talk about context-free grammars a little bit more. So, yes, so you see that in this definition, this notation for the grammar, we have used some specific notations which I have highlighted in red. So we have choices. So a value can be string literal, can be a number, can be an object, an array. This is a choice. An object then needs to have the braces. This is not negotiable, but it can have no pair at all. So you see that there are a pair of parents there, and the interrogation sign means it's optional. The star here means that everything that is in the brace here can appear 0 or more times. So basically, you have pairs separated by commas, and you can have 0 pairs, or you can have many pairs. You're probably familiar with this notation because the same notation has been used for regular expressions. And I think most of you must have used regular expressions at some point, so this should not be too unfamiliar. Now this notation, I've called it the parsing expression grammar notation. I called it the regular expression notation, but here it's used for a grammar, not just a regular expression. We'll see how grammar and regular expression are related together a bit later. But for now, let's go to the parsing expression grammar, and we'll explain exactly what it is in a bit. So another notation that's very popular is the extended Bacchus-Nora form. Bacchus and Nora, these guys, they're famous for their work on Fortran and COBOL, so very old programming languages. what you can see here is that for optionality, we use brackets. So everything in brackets is optional, and everything between braces can enter one or more times. So to go back to here, right, where we had like 0 or more, well, here we need to combine 1 or more with optional, which comes down to 0 or more. Otherwise, it's exactly the same. Okay. So this is extended back to small form, which is an extension of the back to small form. In back to small form, these symbols don't exist. This optional, 1 or more don't exist. So how do we? Well, we use recursions and add some more rules. So let's take the object rule. It's here. So instead of having like this whole affair here, what we end up doing is that we define a new rule called pairs. And pairs is optional, which means it can match epsilon. Epsilon means nothing. Just it doesn't match anything. I could have used an empty pairs of quotes there, but epsilon is the usual mathematical notation for this. Or it is actually some pairs, and some pairs is going to be a pair, and then t pairs is a recursion, which can be either nothing or a column followed by more pairs. So you see that there's a recursion there. This goes back here. So this is obviously less clear, but this is the original notation. And there is some value in this notation. If you're going to define semantic of a grammar, so far we only have a grammar as a description, but we haven't really said what this notation means. This will come later. But it's easier to assign meaning to rules that are as simple as possible, so you don't have all this stuff here, because you need to define the meaning of that too. So simpler is easier to define meaning. And actually, the way grammar formalism is typically defined, it goes even simpler than this, because you don't have the choices. Basically, instead of having, for instance, t pairs is epsilon or a column and pairs, it will be t. You have two definitions for t pairs. One definition for t pairs is that it can be empty, and another definition for t pairs is that it can be a column followed by pairs. Okay, so now we come to the grammar formalism I was talking to you about. So partial grammar spec is a grammar formalism and it's also a notation. What's a formalism? It's a mathematical system to define a language. So remember, language is a set of sentences, a mathematical set. And notation is a way to denote, describe the grammar. And this grammar that's been written using notation will be interpreted by the formalism. And here we mean by interpreted, we mean that the formalism will give meaning to the grammar by basically saying, okay, with this description, here is the language, the set of sentences that this grammar denotes. Okay, so formalism is the way to go from notation to the set of sentences in the language. So traditionally, well, the back notation is used for parsing expression grammars. So that's one formalism. Another formalism that's even more popular is context-free grammars. We'll talk a lot about them in this course. And traditionally, the back notation, back form is used to denote context-free grammars. CFG and PEG are similar, but they are different. That's very important. I'll repeat that later. Indeed, it's next slide. So CFG and PEG are different formalism. And that trick with the example, because the JSON example is very simple. And for them, actually, the PEG and CFG grammars, they look more or less the same. So basically, the semantics are different, but the result of applying them on the grammar is the same. This is not true in general. There are very important differences between CFG and PEG, and we'll explain them later in the course. Right now, we're just doing light introduction. I think there's already enough concept floating around to confuse further, but keep in mind, for the rest of the course, CFG and PEG are not identical, they're different. So I said EDNF is usually a notation for CFG, and the PEG notation is usually for PEGs. The thing is, it's just notation, it's just a matter of convention, okay? So as long as you define a way to map the notation to the formalism, you can use any notation you want. You just need to say what it is you mean by your notation, okay? And you can invent new notation, etc. That's not the point of the course, but I sometimes see people arguing very strongly about, oh, you use this symbol, and that's for this formalism. Well, no, it's just if I say that this means this, I can use it. I can do anything I want as long as it's defined, as long as it's clear what is meant by the symbols that I'm using. Okay, so what I'm presenting to you is convention, but this makes sense, you can do whatever you want. Okay, so this was a bit of a dense theory segment. Next time, I'll give you some background on parsers, and we'll see that parsers and the grammar, and we'll learn all about that. Welcome back, friends. Today, we're talking about parsers, really the practical sides of it. So let's
Yeah, I think I'm gonna do this or read this stuff here. I think I'm gonna spend another hour, maybe 1 hour and a half, to try to reach 5 hours. I put the timer for 1 hour and a half. So I think the main thing that I'm thinking about is it's not even about the compilers or the parsing, it's more about what exactly what things exactly would be good to put on to create a visualization for. And I think that the main thing that I'm thinking about in my mind now is how to track the value of a variable during the execution of a script or a software program. But the biggest challenge with that is that, and I think this is the main thing that I'm thinking about, is you have the name, which is an arbitrary name that people give, and then you have what the thing actually is and what it becomes during the program. So the same variable can become multiple different names during the program, and the main thing that is going to change is the scope. So the way that is being passed around from functions, and what the functions are returning, and that kind of stuff. So the question that I have is how can I capture the underlying layer and how the variable is changing over time. But it's really hard to think about. And the other thing is that, like, how can you remove all the differences in arbitrary names that people give for variables, but at the same time make it so that you understand like how to use the library? Because this is the problem, is that you need to know the names regardless to be able to learn the library. So I can't completely remove because one idea would be to put everything on a lower level abstraction, let's say. So instead of making variables, you can make like variable 1, variable 2, just a placeholder, and then you can display the logic, and then every software would be the same because it would all boil down to that common denominator. But then obviously the issue with that is that even though it may allow you to understand and learn things a lot faster, you're still not gonna be able to use the APIs in the software because it requires you to know the differences in names. So the challenge and the question is, how do you make something that allows you to see the underlying fundamental structure, but at the same time makes it easier for you to learn the thing faster? And this is the main thing that I'm trying to think about. But I think probably what I'm going to do is just break down into a bunch of different things, like a bunch of different folders here, and create a bunch of different projects. And I think that the best thing to do is just to play around and try to build a bunch of stuff and see like what kind of things would work. And then the more I do it, the better I'm going to become, and the easier it's going to be to figure out something that actually is useful. So I'm gonna have to read this out loud, I think, because the text-to-speech doesn't work on this page. But maybe I can paste this on another website and then just put the text-to-speech. Actually, it might be better to just read out loud because it's gonna force me to pay attention to everything. But I'm kind of tired of talking already because we talked a lot today to explain everything. Today we're going to write a compiler together, but not just any compiler, a super duper teeny tiny compiler. Compiler is so small that if you remove all the comments, this file would only be 200 lines of actual code. We're going to compile some Lisp-like function calls into some C-like function calls. This is actually kind of sucks because I thought it would be about JavaScript since the file is in JavaScript, but whatever. I think it's still good starting point. I think the first project that I'm gonna do is probably gonna be to create an abstract syntax tree or something like that, and then visualize the abstract syntax tree like I did with Python already, like the whole. But I want to do it more like instead of having to run the code, I want to create something that parses the files instead, because I think that running the code adds additional layers of complexity, and that it's kind of annoying. I think eventually I want to get to the point where I'm going to run the code, but I think before it's probably better to try to do something that just by reading the files and seeing the characters, it allows you to understand what's going on. I think that's the main goal that I have. So how can I, because it's really, and it's a massive problem that I had ever since I started learning how to code. Like you get to these projects and there's a bunch of different files and folders, and it's just a waste of time. And I always felt like it doesn't have to be that way, because it's not very hard to actually understand what's going on. Like the biggest part that is annoying is just trying to see how everything is connected. And a lot of times it's confusing because either there is no clear link between functions or variables, or just because it's like a bunch of different functions calling each other and you have callback functions and stuff like that. So like in order to keep track of everything, it just takes a lot of time. I think the React code is a great example of this. Like, the most annoying part of understanding is just the global variables that they use to keep track of the lanes and to keep track of and also the callback functions that they set to perform work. So if there was a way to just quickly see how these variables are being used throughout the entire code, I think it would be a lot easier to understand what's going on. So, and hopefully, but this is another problem. I think another fundamental thing that I'm thinking about is that, like, and I think this is one of the biggest issues with just trying to parse the files, is that the problem is that most code, probably all the code that exists, it's always dependent on the data. Because I think the main function of code, the main purpose of code is to provide a structure to shape data. That's what the essence of code. So all the code that exists is going to be based on shaping some data across a structure. So if you're just looking at the files or you're just looking at the structure, you need to simulate the data to see in how many different ways the logic of the code would change depending on the data, because it's going to change the flow of the if-else statements and the loops and also the function calls, which are the main thing, and also the scopes as well. But so the problem is that I think that I can't think about an easy way, because then the issue is that it's going to depend on each application, what kind of data it receives. So like one way would be like to create a set of template data. Maybe this is a good way to go about it, actually. Like, I can create a massive data set of different types of data structures. Because at the end of the day, the fundamental data structures are always going to be the same. And then more complex data structures are always byproduct of the simple data structures. And actually, you can make the argument that everything is a data structure, because it's pretty much... because at the end of the day, it's going to be the same thing at the bottom layer. Like, data and algorithms are the same thing. They're just separated through the reference frame of identity that creates the illusion of the symmetry between the two. So it's always the shape of the patterns in the electromagnetic field. So everything is going to be a consequence of, I think the main fundamental ones are for loops, if-else statements, and functions. I think those three are the core essence of everything. And then obviously scope, but the scope is pretty much function. It's the same thing. So I think that all code that exists boils down to these three things, I think. And then everything else is built on top of these principles. So you have more stuff like the switch or the closures or decorators and polymorphism and stuff like that. And the different types of data, like integer, float, or string. But all of those things are based on if-else, loops, and functions, I think. So I guess one thing that I could do is just create a data set that has a bunch of variations of different types of data. And then I can run the code, but not run the code, but simulate like the running of the code through the data. Which would be which probably would be the same thing, because you can argue that is the same, but the difference is that in that case I would control the input. So I think that's the difference. So I create a simulation for running, and then based on all of the inputs of the data, I can create like a multidimensional graph, let's say, that would capture like the variance of how the code behaves in relation to the variance of the data. And then I can create a profile of that and combine with all of the other code, and then create a funnel that optimizes the efficiency in understanding what's going on. We're going to compile some blah blah blah. If you're not familiar with one or the other, I'll just give you a quick intro. Actual functions add and subtract, they would be written like this. Add, subtract. So pretty much the same. Oh, the difference is the comma here. Yeah, comma. That's pretty much it. Well, good, because this is exactly what we're going to compile. Well, this is neither a complete list for C syntax. It will be enough of the syntax to demonstrate many of the major pieces of a modern compiler. Most compilers break down into three primary stages: parsing, transformation, and code generation. Parsing is taking raw code and turning it into a more abstract representation of the code. Transformation takes this abstract representation and manipulates to do whatever the compiler wants it to do. Code generation takes the transformed representation of the code and turns it into new code. Parsing. Parsing typically gets broken down into two phases: lexical analysis and synthetic analysis. I think I'm just gonna copy this stuff. Another thing that I realized after learning a bunch of stuff is that one of the main things is keywords. And I think this is one of the hardest parts. Like when you're beginning something, if you don't have like any mentors or anyone to like present the way, the hardest part is gonna be figuring out what is the keywords that are important, because you don't know what you don't know in the beginning. So it's like a paradox that in order to learn something efficiently, you have to understand what you don't know, because you need the keywords. And the keywords are the bridge between this. So I think this is very important to. And also it reminds me of some question that I saw on a stream. I think like someone was asking something along the lines of whether or not you want to have the answer to all the questions, and then I said that I prefer to have all the questions. And thinking about it is pretty much the same thing, because it's a symmetry. So like in one way to look at it, having the answers is better, because you don't have to do the work. But if you're assuming the reference frame of space-time, then you have the asymmetry, which means that the essence of cause and effect relationships are always going to be the question first and the answer later, because that's the arrow of time, that's the direction of time. So having the answers to all the questions keeps you stuck on the same paradigm you're at, because the answers just solve the current paradigm. And what creates new paradigms are the questions. So if you take into consideration the cause and effect relationships and the reference frame of space-time, then having the questions is always better, because it means you're always ahead, because they come first. But obviously they are codependent, so it depends on the way that you look at it, because it's relativistic, so they are the same thing in one way of looking at it. But yeah, I think that this is why it's very important to have the keywords and also try to formulate good questions based on the keywords, because I think that allows you to learn faster. Lexical analysis takes the raw code and splits it apart into this called tokens by a thing called a tokenizer or lexer. Tokens are an array of tiny little objects that describe an isolated piece of the syntax. That they could be numbers, labels, punctuation, operators, whatever. The other thing that operators are also something that is fundamental. I think is actually even more fundamental probably than. I think it is more fundamental than if, else, loops, and functions, because it's pretty much the base of everything. So I think another thing that I'm gonna do is rewatch the Ben Eater playlist. I think I already watched that playlist like 3 times now, but it's really good. Is this one?
Ever since I uploaded.
And maybe another thing that might be interesting to do is just go back to playing Turing Complete, which is a game that allows you to build a computer from scratch just using logic gates. But maybe I'm just gonna look at the solution for that because it's very difficult, takes a lot of time, so I don't want to spend. And it's not like, I think it would help me, but it's not a direct thing. So it's more like long-term payoff, I think, playing through and complete. To understand how assembly is built with logic gates in the beginning. 'Cause I think this is the hardest part, is the jump from machine code to assembly, because it takes in understanding the operational system to understand that, and that's a problem because the operational systems are very complex. So I think on the playlist, if I remember correctly, the most basic form, you create the program counter first, and then you pass things between the registers with the program counter. But I'm pretty sure in operational systems that there are a lot more things, and like the only downside of this playlist is that the jump he makes from the binary is not like, it feels like he's missing some things, I think. Because he jumps directly from binary to using assembly at some of these videos here, and that part, it was a little bit confusing for me. But I think I'm gonna watch this stuff to get again. Synthetic analysis takes the token and reformats them into a representation that describes each part of the syntax and their relationship to one another. This is known as an intermediate representation or abstract syntax tree. An abstract syntax tree, or AST for short, is a deeply nested object that represents code in a way that is both easy to work with and tells us a lot of information. For the following syntax, tokens might look something like this. And an abstract syntax tree might look like this. So just a tree with the tokens. Transformation. Next type of stage for a compiler is transformation. Again, this just takes the AST from the last step and makes changes to it. You can manipulate the AST in the same language, or you can translate it into an entirely new language. Let's look at how we would transform an AST. You might notice that our AST has elements within it that look very similar. There are these objects with a type property. Each of these are known as an AST node. These nodes have defined properties on them that describe one isolated part of the tree. We can have a node for a number literal, or maybe a node for a call expression. When transforming the AST, we can manipulate nodes by adding, removing, replacing properties. We can add new nodes, remove the nodes, or we could leave the existing AST alone and create an entirely new one based on it. Since we're targeting a new language, we're going to focus on creating an entirely new AST that is specific to the target language, traversal. In order to navigate through all of these nodes, we need to be able to traverse through them. This traversal process goes through each node in the AST depth first. Yeah, one thing that is difficult to find resources is like this part of going from the binary to the assembly the first time, because of this program counter stuff in the registers. I need to figure out how. Maybe I should ask ChatGPT for keywords. I think that's what I'm gonna do now. And well, let me think. Because the main thing here obviously is that, like, how would you create the AST if you only have machine code? But I guess it's just gonna be, the other thing I'm thinking about is if I should probably try to memorize the letters to numbers, and also train a little bit on the conversion between binary and decimals, because I suck at it. But I think that would help me to understand more, or to think more about it, like in terms of numbers, because this is one of the hardest parts as well, I think. Like, we see everything in letters, but everything the computer is doing is calculating numbers, and it does it on binary. So I think being able to think about letters as numbers is probably very helpful to understand more. So for the above AST, we would go program starting at the top level of the ST, call expression, add, moving to the first element of the program's body, number literal, moving to the first element of call expressions params, call expression, subtract, moving to the second element of call expressions params, number literal, moving to the first element of call expressions. If we were manipulating this ST directly, instead of creating a separate AST, we will likely introduce all sorts of abstractions here, but just visiting each node in the tree is enough for what we're trying to do. The reason I use the word visiting is because there is this pattern of how to represent operations on elements of an object structure. Visitors. The basic idea here is that we are going to create a visitor object that has methods that will accept different node types. When we traverse our AST, we will call the methods on these visitors whenever we enter a node of a matching type. In order to make this useful, we will also pass the node and a reference to the parent node. However, there also exists this possibility of calling the things on exit. Imagine our tree structure from before in list form. Wrong call expression, number literal, call expression, number. As we traverse down, we're going to reach branches with dead ends. As we finish each branch of the tree, we exit. So going down the tree, we enter each node, and going back up, we exit. So program pretty much is going that first search, and then it just exits when it reaches the base, and then it goes back up. In order to support that, the final form of our visitor will look like this. Enter, exit. Code generation. This also makes me think about the whole thing, like about the fundamental physics and understanding behind computing, and behind not just computing, but the meaning that comes from computation, which is language. So there's always this connection between, but I'm not really sure if it makes sense, sure. Because it seems like everything is always a tree, and it is that way because it's a hierarchy, and that's how gravity transforms into time, maybe, through perception. So like the nature of symbolic representation is a hierarchy, and that creates the illusion of time, which is computation. So space-time is computation, it's just reduction of infinite potential. And it's hierarchical by nature, but at the same time, like it's a spiral because it's a cycle. So it's a tree and a cycle at the same time, which creates a spiral, which is the pattern of gravity, and that's probably the pattern of perception. And that's the frequency of wave function that creates space-time. But maybe not, yeah. It's very hard to think about this stuff. I think I'll be right back. I think I know one thing I can do to not read this and use the text-to-speech. I'm just gonna copy this stuff and put on ChatGPT. Then I can highlight and read with the text-to-speech. But I think I'm gonna try to go like more. Problem is already tired today of saying a bunch of stuff because there's so much to explain in the beginning. Hopefully it's not very confusing. Because there's so many things that's like, and it's kind of, it's hard to explain when I haven't streamed for a long time, because then like in my mind I'm already someplace, but then like the last time I streamed was way before and I thought about a bunch of stuff, but I haven't necessarily like came to the conclusion or clarified the stuff that I went through to solve the problems. It's still like confusing, but try to explain.
Writing a compiler for a language in the same language is indeed possible and is known as bootstrapping or self-hosting. This concept might seem counterintuitive at first, but it is a fascinating and practical approach in computer science. Here's how it works. Initial version. The initial version of the compiler is written in another language. For example, if you want to create a compiler for language X, you could write the first version in language Y. Basic compiler. The initial version of the compiler is used to compile the source code of language X written in language Y. The output of this process is a basic version of the compiler, which is now capable of understanding some subset of the language X. Refinement and expansion. With the basic version of the compiler in hand, you can now use it to compile more complex and expanded versions of the language X, including new language features and improvements. Iterative process. You keep repeating the process of using the compiler written in language X to compile a more advanced version of itself until it becomes fully capable of handling the entire language X. At each iteration, the compiler becomes more powerful and feature-rich. Stabilization. Once the compiler can handle the entire language X and is self-sufficient, you can stop using the initial version written in language Y. The compiler is now considered self-hosting and can be used to compile itself and other programs written in language X. Bootstrapping has several advantages. Simplicity. It simplifies the development process by allowing you to reuse the same codebase for the initial and final compilers. Trustworthiness. By compiling the compiler with itself, you can ensure that the behavior of the resulting compiler is consistent with the language's specification. Portability. It allows you to easily port the compiler to different platforms, as long as the language is supported on those platforms. Language evolution. As the language evolves, you can adapt the compiler to handle new language features using the same self-hosting process. Teaching and learning. Bootstrapping is a great educational tool as it demonstrates the power of compilers and self-replication. One classic example of a self-hosting compiler is the GNU Compiler Collection, GCC. GCC, initially written in the C language, became self-hosting over time and can now compile its own source code, along with programs written in the C language itself. Bootstrapping is a remarkable achievement in computer science and a testament to the versatility and power of programming languages and compilers. Free research preview. ChatGPT.
So here's the thing, and it is some stuff that I'm thinking about is like if you the main fundamental difference between programming languages is the representation that they have, and I guess it's just because of, like it is because of this cycle, because it deviates towards something completely different. It's like learning two different normal languages. Like instead of learning English, you learn German. Like the conclusions you're gonna get to are very different in both languages. They're always gonna be similar, but they are different because the hierarchy of construction of meaning is different because you're encoding information in different symbols. And I think that's the fundamental difference between the different programming languages. So when you use these abstract symbols you created to compile the language and closing the loop and creating this feedback cycle here that ChatGPT talked about, is like over time you're just gonna deviate more and more depending on the initial position you started from. So like the more you go in the different directions, the more differences there are going to be between the languages, because it builds itself on top of the network. But then the thing that is kind of hard to think about and interesting is that, like, because I also think of mathematics as being the same thing. Like mathematics is just a language, and it is the abstract representation of physical reality through the human perspective. So the computation itself is the exemplification of this hierarchy of symbols that the human experience projects into the computer, because what we are manipulating is the configuration of the electromagnetic field through geometry. So you set up the geometry in a certain way that is going to create meaning over time based on the impulses that go over the geometry. And the fundamental essence of that is mathematics, I think. But the question is whether or not, because the way that I think is just a projection, and like in ultimate reality there's an infinite amount of potential. So mathematics itself is not absolute, it's just a projection. So if that's true, what it means is that 1 + 1 not always equals 2. That's the thing, because 1 plus 1 is just the geometrical representation of a reference frame over infinite potential, and that's the essence of space-time. So you can see that the mathematics and geometry is just a synchronicity of the coherence of an electromagnetic network that creates meaning. But then how do you get out of that? Because it is a paradox, because it has to create meaning over time, but time only exists based on the network. So like it is I think you can't go beyond that, because it's the whole thing about the compiler. Like you can only make conclusions based on the language that you evolved from, which is already the essence of space-time. So it's like a human being trying to ask questions to understand the universe is like creating a compiler based on binary, and then using the compiler to determine the language. You're never gonna get to the bottom. You just create new cycles, which create different abstract representations of the symbolic representation of a network that computes. But I think that mathematics is also that, like, and it is also a projection of space-time, a projection of perception over awareness, which is the essence of space-time, which is a multifractal hologram, which is a paradox, singularity paradox. Code generation. The final phase of a compiler is code generation. Sometimes compilers will do things that overlap with transformation, but for the most part, code generation just means take our AST and stringify code back out. Code generators work several different ways. Some compilers will reuse the tokens from earlier, others will have created a separate representation of the codes so that they can print nodes linearly. But from what I can tell, most people use the same AST we just created, which is what we're going to focus on. Effectively, our code generator will know how to print all of the different node types of the AST, and it will recursively call itself to print nested nodes until everything is printed into one long string of code. And that's it. That's all the different pieces of a compiler. Now that isn't to say every compiler looks exactly like I described here. Compilers serve many different purposes, and they might need more steps than I have detailed. But now you should have a general high-level idea of what most compilers look like. Now that I've explained all of this, you're all good to go write your own compilers, right? Just kidding. That's what I'm here to help with. So let's begin. The tokenizer. So I think this stuff that I was talking about just now is related to the stuff that I saw on reading Vitalik's articles on Ethereum about the modular arithmetic that is used to create private and public keys. I think that's one example of why this is interesting, because I think that, and I still don't understand very well how that works, but I think what they pretty much created is the stuff that I'm talking about, where they created a different language for mathematics, let's say, because instead of using the normal way that mathematics works, you keep the rule set, but you change the abstraction that you built on top of it, and that gives you modular arithmetic, which is based on the shape of the elliptic curve. So I think that it might be possible to create like different types of mathematics if you build meaning on top of different rule sets, but like not on top of different rule sets, but build meaning on top of different. And this is what the stuff that I can't quite put words, but I think that there's something there. And I think that modular arithmetic would be like, it's like analogous from, like, let's say normal mathematics is Python, and then modular arithmetics would be JavaScript, or vice versa. So it's just a different programming language, because it's like the same structure, is binary or mathematics, but it's using a different structure to build meaning on top of it. And that allows it to have different functionalities, and I think that's the thing, because on the essence of mathematics, you always assume, like you assume that answers are correct, and I think that's just an assumption that we give. Because what exactly is mathematics? Like, if you think about it, and I think it just is like so ingrained into the way that we think that we don't question anymore. I think a lot of people question, but like a small part of people question, but not most people don't. They just take it for granted because they don't even realize that they are doing that. But yeah, if you think about it, mathematics is just a connection of space-time. Like, you're assuming a cause and effect relationship between reference frames, and that's what the Cartesian coordinates are. But even more abstract mathematics that goes more than 4 dimensions, you're still assuming the connection. So I think like it's just a way to encode information in symbols and based on logic. But what even is logic? That's the thing. And I think the value of thinking about these things is this stuff about, because it allows you to build more things. And I think that's the thing, like, because all the systems we build are on the assumptions of and obviously it seems to work, so something is right. It seems to be right, but maybe it's not like the limit, if you think about it. Because like, you're using this framework to build a bunch of systems, and then the systems work. And like, then you can say like, well, like the laws of physics never lie, but maybe if you change the framework, then it allows you to have quantum leaps in innovation. But I think that the jump from modular arithmetic to normal arithmetic is not this quantum jump, because it's still using the same thing. And I think it might be impossible to have a new form of mathematics, because that would mean that you break space-time. So that means you're not the biggest problem is, how do you find the bridge? That's the thing. Like, even if it was possible, because there would be loss of information, because by definition the only way to exist in space-time is if you are projecting that logic into it, which is the connection of geometry, which is mathematics. So even if you manage somehow to go to like a different reality that has a different rule set, and then you make different information, how would you bring back? Like, it's impossible, because it's inconsistent, because reality is just about the reference frame. So, but I think even under the constraints of mathematics, it might be possible to instead, because if you think about it, and this is another thing that I was thinking about the other day, it's like, the further in mathematics you go, all that is happening is that you're creating more symbols. So like that's the whole evolution of mathematics, if you think about it. And the reason why is because there's something more fundamental there. That's the thing. Is because the symbols themselves are like the projection of the fundamental thing. But I can't quite put, because logic, I think, is not very, very accurate thing to say, I think. There's something more fundamental that I think that people take it for granted, and that leads, like, makes everything go towards this direction. I think the way to maybe explore different possibilities would be to question this assumption. Like, how do you make it so that you can encode information in symbols in a different way? I think that's the thing that I'm trying to figure out. So like, instead of using the same symbols, because it's just like programming, so instead of just building on top of the same symbols, the same, which is mathematics, how can you break down into the geometrical essence of that framework, and then from that point build new structures? And I think that the answer to that might be through the numbers. Now that I think about it, maybe that's what computing does. Like, that computing is just a different reference frame of mathematical representation, if you think about it. And maybe there are other ones, but it's hard to think about. Because one thing that I'm thinking about, that I've thought about for, I've been thinking about for some time, is the numbers, like the 0 to 10, 0 to 9, is just different symbols. So like, why is 2 and not 4? Like, it's a symbol that captures something about the universe. And I think the thing that captures is a multifractal essence. And I think it has to do with the complexity of the biosphere of the current present moment in time. So like, there's encoding of information because each symbol is a multifractal representation. So I think like the reason why is 9 different symbols that always repeat themselves in different intervals is because of the systems we have, which is the decimal system. But then you think about it, like, why is it like that? Why not have a different way to represent, like a different symbolic representation that would create a different mathematics? And I think that in some ways that is the evolution of mathematics. Because in mathematics you have alpha, beta, like all of this sum symbol, and you just put more and more. So, but I think that maybe there is a way to, instead of just putting more symbols, you break down the structure into different intervals, let's say. So instead of using 9 numbers, for example, use 5. And then maybe change the symbols so that is not your assumptions are not projected from the subconscious to think about it in the same way you think about decimals. But, and I think binary is that in some, like, in a way. It's just changing the frequency of the multifractal structure. So binaries use zeros and ones instead of 0 to 9. And that changes the way that the thing that it produces, because it's both 0 to 9 and 0 to 1 are multifractal representations of the structure of space-time in relationship to a current reference frame. And I think that depending on which reference frame, which structure you begin, you create a different abstract representation. Yeah. We're gonna start off with our first phase of parsing lexical analysis with the tokenizer. We're just going to take our string of code and break it down into an array of tokens. We start by accepting an input string of code, and we're gonna set up 2 things. A current variable for tracking our position in the code like a cursor, and a tokens array for pushing our tokens through. We start by creating a while loop where we are setting up our current variable to be incremented as much as we want inside the loop. We do this because we may want to increment current many times within a single loop because our tokens can be any length. We're also going to store the current character in the input. The first thing we want to check for is an open parenthesis. This will later be used for call expression, but for now we only care about the character. We check to see if we have an open parenthesis. If we do, we push a new token with the type paren and set the value to an open parenthesis. Then we increment current and we continue in the next cycle of the loop. Next, we're going to check for a closing parenthesis. We do the exact same thing as before, check for a closing parenthesis and add a new token, increment current, and continue. Moving on, we're now going to check for white spaces. This is interesting because we care that white spaces exist to separate characters. But it isn't actually important for us to store as a token. We'll only throw it out later. So here we're just going to test for existence, and if it doesn't exist, we're going to just continue on. Maybe another thought about this stuff about mathematics is that it might be the case that language itself, besides mathematics, is just this stuff that I talked about. I think it probably is the same thing. The reason why languages exist is because it allows you to tap into different frequencies of abstract representation of space-time. So language is logic. I think that's probably true. You're just encoding information, just in symbols. Yeah, but it's hard to think about because there's something that I don't understand really well. I think it's the fundamental nature of mathematics, because the difference between mathematics and languages would be obviously the operators. So what exactly does that mean? This is very hard for me to think about. Next type of token is a number. This is different than what we have seen before because a number could be any number of characters, and we want to capture the entire sequence of characters as one token. So we start this off when we encounter the first number in a sequence. We're going to create a value string that we are going to push characters through. And we're going to loop through each character in the sequence until we encounter a character that is not a number, pushing each character that is a number to our value and incrementing current as we go. After that, we push our number token to the tokens array. And we continue on. We also add support for strings in our language, which will be any text surrounded by double quotes. We start by checking for the opening quote. Keep a value variable for building up our string token. You skip the opening double quote in our token. Then we'll iterate through each character until we reach another double quote. Skip the closing double quotes and add our string token to the tokens array. Last type of token will be a name token. This is a sequence of letters instead of numbers. That are the same. They are the names of the functions in our Lisp syntax. Again, we're just going to loop through all the letters, pushing them through a value, and pushing that value as a token with the type, name, and continuing. When we have not matched a character by now, we're going to throw an error and completely exit. Then at the end of our tokenizer, we simply return the tokens array. It's pretty simple. Just parsing everything. For our parsers, we're going to take our array of tokens and turn it into an AST. So we define a parser function that accepts our array of tokens. And we keep a current variable that we use as a cursor. But this time we're going to use recursion instead of a while loop. So we define a walk function. So the walk function, we start by grabbing the current token. We're going to split each type of token off into a different code path. And so first it separates everything, or separates everything into its own type, let's say, and then it puts the logic to see how it's gonna encode the cause and effect relationships. We test to see if we have a number. We have one, we increment current and return a new AST node called number literal asset, and setting its value to the value of our token. If we have a string, we will do the same as number and create a string literal node. Next, we're going to look for call expressions. We start this off when we encounter an open parenthesis. We increment current to skip the parenthesis since we don't care about it in our AST. Create a base node with the type call expression, and we're going to set the name as the current token's value, since the next token after the open parenthesis is the name of the function. We increment current again to skip the name token, and now we want to loop through each token that will be params of our call expression until we encounter a closing parenthesis. Now this is where recursion comes in. Instead of trying to parse a potentially infinitely nested set of nodes, we're going to rely on recursion to resolve things. To explain this, let's take our Lisp code. You can see that the parameters of the add are number and a nested call expression that includes its own numbers. Add true, subtract 4, true. You also notice that in our tokens array, we have multiple closing parentheses. We're going to rely on the nested walk function to increment our current variable past any nested call expression. So we'll create a while loop that will continue until it encounters a token with a type of paren and a value of closing parentheses. We call the walk function, which will return a node, and we will push it into our node params. Finally, we will increment current one last time to skip the closing parentheses. Again, if we haven't recognized the token by now, we're going to throw an error. Now we're going to create our AST, which will have a root, which is program node. And we're going to kickstart our walk function pushing nodes through our AST body array. The reason we're doing this inside a loop is because our program have call expression after one another instead of being nested. At the end of our parser, we return the AST, the traverser. Let's see how long still have. So 700. That's almost done. I think I'm gonna finish. I'm already tired of reading, but I think I'm gonna finish. I think I'll be right back. Let me drink something. Tired of talking. I'm gonna try to finish this and then I'll stop streaming. Then go back another time, probably. I think I'm just gonna watch the videos off stream. Not sure. If I stream tomorrow, I think I'm not gonna do much today. So if I stream tomorrow, I'm probably gonna come back at this point. Maybe start trying to build something simple. But if not, I'm probably gonna maybe if I stream tomorrow, I try to change the, or I might change off stream this stuff here so that it works with the layouts. After this, I still have to make the context. Maybe I'll do this tomorrow on stream. Yeah, I'll be right back. The traverser. So now we have our AST and we want to be able to visit different nodes with a visitor. We need to be able to call the methods on the visitor whenever we encounter a node with a matching type. So we define a traverser function which accepts an AST and a visitor. Inside we're going to define two functions. Traverse function that will allow us to iterate over an array and call the next function that will define traverse node. Traverse node will accept a node and its parent node so that it can pass both to our visitor methods. We start by testing for the existence of a method on the visitor with a matching type. If there is an enter method for this node type, we'll call it with the node and its parent. Next, we're going to split things up by the current node type. We'll start with our top level program, since program nodes have a property named body that has an array of nodes. We will call traverse array to traverse down into them. Remember that traverse array will in turn call traverse node, so we are causing the tree to be traversed recursively. Next, we'll do the same with the call expression and traverse their params. In the case of number literal and string literal, we don't have any child nodes to visit, so we'll just break. And again, if we haven't recognized the node type, then we'll throw an error. If there is an exit method for this node type, we'll call it with the node and its parent. Finally, we kickstart the traverser by calling traverse node with our AST with no parent, because the top level of the AST doesn't have a parent. The transformer. Next up, the transformer. Our transformer is going to take the AST that we have built and pass it to our traverser function with a visitor, and we'll create a new AST. So original transformer. Sorry, the other one is longer. It doesn't seem that complicated, to be honest, but obviously this is probably the simplest version, so there are probably a lot of optimizations, but I think I'm not gonna, because my main goal is not to create an interpreter or compiler. I'm just studying this stuff so I think I'm gonna especially spend time on the JavaScript and Python ones, because obviously I want to understand how they work so I can think about different ways to extract information. But my main goal is obviously not to create a compiler or interpreter, just to understand what is the best way to get information from the languages, from code, so I can visualize later. So we have our transformer function, which will accept the list AST. We'll create a new AST. We create a new AST, which, like our previous AST, will have a program node. Next, I'm going to cheat a little and create a bit of a hack. We're going to use a property named context on our parent nodes that we're going to push nodes to their parents' context. Normally, we would have a better abstraction than this, but for our purposes, this keeps things simple. Just take note that the context is a reference from the old AST to the new AST. We'll start by calling the traverser function with our AST and visitor. The first visitor method accepts any number literal. You visit them on enter. We create a new node also named number literal that we will push to the parent context. Next, we have string literal. Next up, call expression. Start creating a new call expression with an nested identifier. Next, we're going to define a new context on the original call expression node that will reference the expression's arguments so that we can push arguments. Then we're going to check if the parent node is a call expression. If it is not, we're going to wrap our call expression node with an expression statement. Do this because the top level call expression in JavaScript are actually statements. Last, we push our possibly wrapped call expression to the parent's context. At the end of our transformer function, we return the new AST that we just created, the code generator. Now let's move on to our last phase, the code generator. The code generator is going to recursively call itself to print each node in the tree into one giant string. We will break things down by the type of the node. We have a program node that we will map through each node in the body and run them through the code generator and join them with a new line. For our expression statements, we will call the code generator on the nested expression and we'll add the semicolon. For call expressions, we'll print the callee, add an open parenthesis, we'll map through each node in the arguments array, and run them through the code generator, joining them with a comma, and then we'll add a closing parenthesis. For identifier, we'll just return the node's name. For number literal, we'll just return the node's value. For string literal, we'll add quotations around the node's value. And if we haven't recognized the node, we'll throw an error compiler. Finally, we will create our compiler function, and here we will link together every part of the pipeline. Inputs, tokenizer tokens, tokens parser, AST transformers, transformer and UST generator output. So tokenizer simply return the outputs. Now I'm just exporting everything. Yeah, interesting. I'm gonna copy this stuff and make a file here. Probably gonna look at this later as well. I think that the parts that are gonna be most useful for me is probably gonna be the AST stuff, the parsing and the tokenizer, I think. The rest is not that important, but maybe it is. Not sure. So I'm not sure when I'm gonna come back, but I'm probably gonna continue to do this stuff. If I come back tomorrow, I'm probably gonna just work on this thing here. I'm gonna fix the position, try to fix the position so that the layout works with the stuff that I have, and then maybe create a custom component to just see if I can change the values of the nodes and the edges, the size. I'll also have to implement the raycaster. Maybe I'll do that. Yeah, maybe I implement the raycaster. I think I'm just gonna watch I'm gonna try to watch a bunch of videos, this playlist again. And then, yeah, read articles and probably try to do, because I don't know very well, what is the best direction to go to get the most meaning out of the code. I'm just gonna do a bunch of stuff, I think. So the first projects that I do is probably gonna be parsing files, I think, and then seeing if I can build a graph based on them and then put on the visualization. So yeah.